intersection problem, and that was the last thing we did. Shall I just continue with the problems, or have there been more? Before anything, we have to. Well, we'll just wait for Tyrese and George before I bring up the challenge. Actually, so we'll just do a question or two while we're waiting for them. So I'm gonna have. They're usually late, eh? So okay, I'm gonna go up to some of the old questions. Did we do this question? This question we did, right? Yeah, we did this question. Yeah, you got it. What part of like 4 o'clock did you not understand?
There's so much traffic.
Oh yeah, blame the traffic, huh?
I'm joking.
Yeah, that was a very funny joke.
Sorry.
Why fuck you late?
I had to use the bathroom.
No, I'm just kidding. It's just Chanel put me up to this. I wasn't actually going to tell you off. Sorry, I can't keep it going for that long. I'm just kidding. How you going, Tyrese? You doing alright?
I'm so good.
Yeah? Good time. Did I scare you at least a little bit?
Yeah, I was like, how do I say I need to take a shit?
Yeah, I had to take a shit before. This is on YouTube now. There's no such thing. There's no such thing as TMI. We did this one too. I'm just trying to figure out where we sort of left off. Were there any that I missed that anybody had posted that you wanted me to take a look at? Was this one of yours?
No. That one we already did.
Did we? I don't remember doing that one. What about this one? We did this one. Yeah. We did this one. So I've gone back too far.
Is that Mark?
Yep.
Okay. I've got 42. Yeah, 42.
Oh, I think this is yours, right? We did this one. Chanel, this one was yours, right?
Yes.
And so this one we might not have done. Yeah, no, this one no, and then this one no, and then this one. Did we do that?
No.
Okay, cool.
Muscle search. I got rank 2 with that as well.
We got much better. Rank 3 was full.
No, like the average is usually a fail for the trials. All right, let's continue. Let's go, friends. Okay, so find the shortest distance between the lines R1 and R2. Okay, so there are 2 lines here. So this is always, you guys were saying that 3D geometry sort of fucks with you guys a little bit, eh? So let me show you a bunch of ways that we could do this. Like it's always fun to see a bunch of different ways to visualize this. Now the first thing I want you guys to practice doing when you're solving any 3D geometry problems is bring pens into class with you. Okay, like please bring pens into class with you. So let me show you, let's just try to do this. Can I borrow 2 of your pens, Blake? Arigatou gozaimasu. All right, please 2 pens. Are you Japanese as well? Nice to know what you think of him deep down. Okay, no. Okay. So, but anyway, pretend you have 2 pens here. These 2 pens represent 2 lines. Okay, and so let's imagine they're oriented randomly relative to each other. And we're going to say, okay, how do I know when they're at their closest point? How do I know when they're closest to each other? So actually, sit there with your pens and look at what happens as I'm moving them around. Okay, so just think about it. When are they closest? Like, what can you tell me about the point where they're closest? Can you say that they're perpendicular? Can you say that they're like, what can you say? Can you say that maybe their angles are 30 degrees to each other? Like, what can you say in general? It's always good to see it in 3D. Once you see it in 3D, then you can't like unsee it. You just have to see it once. Okay? So what can you see? Right? You all got it? So what do you see? So do you struggle to see anything? Do you like? Are you guys struggling to see the condition or not? So I'm gonna go into Desmos 3D because you just need to see it. Once you see it, it's easy. But if you don't see it, then you're screwed. That's the big big thing that tends to happen with these things. All right. So let's try to play this game for a moment, right? So first, for starters, I want to ask you the question: how is this line even defined? And I think this is an even bigger problem, is that I think a lot of people don't even get that. Okay. So when you define a line in terms of a vector, the idea, I always use the STD form, S plus TD. I made that up because it sounded funny. Okay. So function of time. What's funny, Blake? What? What is it?
I'm not.
Because he just remembers last time he showed up to the doctor's office, it was like STD. Fuck. Anyway, continue. So STD form. S stands for start. Okay. D stands for direction. So actually, there's method to the madness. And T, anyone want to guess what T stands for? Time. You're welcome. Right. Start, time, direction. STD form. Right. Usually they don't call it STD form. I just, I figured start, time, direction, then I arranged the letters in a way that looked funny. So that's what I did, okay? So what we do is, I want you to imagine drawing a line, okay? Drawing a line. The way you're going to draw a line is you're going to pick a place. Is it hot in here? Oh, okay.
Could have just said that.
Let me see. I actually don't think I can turn on the air conditioner, unfortunately. But can you check if the windows are open, and I'll just leave this like open properly. Because I think the aircon is out.
Yeah, where's George?
Yeah, unfortunately the aircon is a no today, but the aircon is a no today, but that's okay. We can leave it open for now. All right, so STD. You pick a place to start. So let's say that I want to draw a random line on this plane, yeah? So you're going to pick a random place to start. Let's call this my starting position. I'll call it S, okay? I want you to imagine that there's some kind of plane here. So there could be some plane like that. And this is there's a vector pointing to S, right? So this is my S vector, right? I've just drawn it in a very light color, barely perceptible, but it is there. Can you all see that? So that's my starting vector. Then what you do is you pick a direction to move in. So let's pretend that I chose to walk in that direction, okay? This is the idea there, right? Now, I want you to think about this. T is going to scale D. Can you all see that? T is going to scale D. So if T was 0, what would happen? Well, you'd just be adding S plus 0, which is just going to put you right here, yeah? This is going to be S plus 1D. This is where we're going to be, right? S plus 1D. This point over here is S plus 1D, or S plus D. And then this point over here would be S plus 2D, wouldn't it? Is everyone following that? So that's going to be your line, right? And then, so this would be S, and this would be S minus D, S plus, or S plus minus 1D, so T is minus 1. Can you all see that? So you're like spanning this line. Again, imagine T is a slider. Desmos slider, right? We always like to imagine this, right? Slider, and you're going to slide T, and there's a function, so let's drop in our function friend. Where are you? Sorry, so here's a function, okay? F, T goes into F, and then it plops out S plus TD. Can you all see that? So it's a different kind of function. So usually you're used to functions that take a number in as an input and give you a number in as the output. Everyone's aware of that? But this one's a bit different. This one's a number in, this is a real number, elements of R. Oh yeah, you are?
Yeah.
Bro, you're like literally 20 minutes late.
Yeah, no, sorry.
Bro. Sorry, no, Chanel put me up to this. I'm kidding, I don't actually care. How you doing?
Good.
Had a good week?
Yeah.
Yeah, that's good. Was that one good? Yeah? It should have lasted longer? Okay, cool. Yeah, I don't know, Chanel just likes it when I put shit on you guys for being late. I don't know what it is.
You're a cool person, Sean. Yeah.
Nah, but all good. Alright, so this is a function from R to R squared. Everyone's cool with that? I'm just not good at being mean. That's like mostly Julian's job. I can't be mean. I'm like the nice brother. Okay, is this fair? So I'm going from R to R squared. Can everyone see that? It makes sense because I'm mapping from a line to a plane. Everyone sees this? Yeah? And this is in general what you're doing when you're dealing with vector equations. So I just want to show you this. So I'm going to do it in Desmos 2D first. Okay? So you're probably aware of this. I was doing this with my kids, my year 10 kids the other day. I was showing them projectile motion. Because you guys are all familiar with projectile motion, yes? So projectile motion, I'll just do it again from scratch for you, shall I? So let's do this. We're going to go here, right? I'm going to, oh, the hell? Sorry. So T is going to be my time. Let me make a capital T equals 0, yeah? So I want a function f of t that gives me a time input and gives me a coordinate out as the output. Everyone's cool with that? So coordinate out as the output, I don't know, let's do t minus, t minus 3, or t plus 3. Let's even do 2t plus 3. And then maybe we'll do 4t let's do 5t squared plus minus 5t squared plus 12t plus 4. Okay, let's think about what this does. At t equals 0, where are we?
3, 4.
Yeah, 3, 4. Can everyone see that? So t equals 0, we're at the point 3, 4. Everyone gets that? So t equals 1, where are we? So you got 5 on the x.
11.
Sure, 5, 11. Everyone's cool with that? So I can plot all of these places. So shall I do that? 0, 1, 2, 3, 4, 5. Cool. Can everyone see what this does? Yeah? Maybe I decrease the spacing. So if I just do 0, 2, 5, it's the same thing. How about I go 0 0.5, now you got more points. 0 0.2, you got even more points. 0 0.1, you got even more points. What does that look like to you? Looks like a parabola to me, right? In fact, if I want to, I can say this guy over here is ux, isn't he? And this guy is x naught, or my starting position, right? This is 1/2 of a t squared, right? And this is u y t, and this is my y naught. These are all my parameters, right? Those are all my projectile parameters, are they not? So, hey, check that out. Now I can control things. Yeah. I can change ux, I can change uy, I can change my acceleration, I can make it as big or as small as I want. Yeah. I can change where I start. Yep. Ux, uy. Everyone's cool with this? I might actually not make this like this. I might actually make it a number 0. I'll start it at time equals 0 and go up to time equals 5. Okay, and I'll click play. And we'll speed it up. Cool. Everyone sees that? It's launched from the point x naught, y naught. Yep. And it's launched in the direction x naught, y naught plus, and then Desmos t is a special variable, so ux, vx. Oh, sorry, ux, uy, I meant. Everyone sees this? So that's the direction I'm launching in. I'm even showing you my velocity vector, yeah? And one other thing Desmos has, which is a nice little trick, is if you just type f of t, it'll just connect it. So that's the path I'm going along. You all see that? So then if you go here, woo, now I can fully control it, see? Full projectile sim right there. Everyone gets how this works? You can choose where to start. So this controls x naught and y naught. So dragging the point around changes x naught and y naught, because that's how that goes, right? And then changing ux changes that. You can shoot it backwards if you want, no problem. If you can also change uy, and that's going to change how fast it goes up or down. You can even just shoot it straight down if you like. And then a is the acceleration, of course. So make the acceleration negative if you like, no problem. So this is a fully, this is a full parametric simulator here. So projectile motion. So I just wanted to show you, it doesn't actually need to just be a straight line. But you notice that this is a mapping from, notice how I have a slider for t, that's r1, or r, just the real numbers. And then the output is a 2-dimensional grid, so it's r squared. Is that cool? And this is the basis of all vector functions. So I'll paste that in for you, just so you guys, if you want to play with that, you feel free to. Okay? So then if we're dealing with this, we're actually going to go back to STD form, right? So let me go here. Let me clear this. And then let's do this. S is going to be my starting vector. Vectors in Desmos, you just write as points. So let's just make that 0, 3. I can drag that to wherever the hell I want. Everyone's cool with that? S. And then D is another vector. Let's say 4, 5. Cool? Now this is going to choose the direction that I'm going to move in relative to 0, right? So then S plus TD, yeah? T is a variable. So if T was 0, where would I be? I'm just at S, right? Let me make this nice and big so you can see it. Let's make that 20, 50. Cool? Everyone sees that? So then as you move, you notice that you're moving that way. Why that way? Because it's in the direction of the D vector. Do you all see that? The D vector, I can actually draw it for you. That's the direction of the D vector, right? So everyone sees that? It goes like that. Then if you just write S plus TD, S plus T little td, because Desmos little t is a special variable, you can plot it out from -10 to 10, and there you go. Sees that? Everyone's got it? Very simple. So this is how you draw lines. Does this story change in 3D? Absolutely not, right? So S is a 3-dimensional point. Let's say 0, 2, 4, right? D is a 3-dimensional point. Let's say 1, 1, 4, 1, 1, 2. Cool. Everyone sees that? I'll draw it for you so you can see it. TD. That's going to be my T. That's going to be the direction I'm going to move in. Yeah. You can move S to -4, whatever, right? So it's going to start there and it's going to move in the direction of D all the time. Got it? So if I type S plus TD, go from -10 to 10, that's my line. Everyone sees it? Cool. Now we're asking the question, how do we figure out when two lines are closest to each other? Right? So I want to really give you visuals, and this is why I said pull up your pens and actually have a look at them, right? If I draw two random lines, so let's call this S1 and D1, right? So this is going to be the first point. This is going to be the first line. So in a folder, I'm going to say the first line. First line. So I'll make everything to do with the first line red. Can I do that? So make everything to do with the first line red. S plus S1 plus T1 and TD1. Cool. Make everything to do with this line red. All right. So that's my first line. Now let's draw another line. Everyone's cool with that? I think there's I could just duplicate this, can't I? I cannot. Okay, that's fine. All right. So let's duplicate this. New folder. So we're gonna go second line. S1 equals, I don't know, give me some random coordinate.
0, 1, 1.
0, 1, 1. Cool. So this time we're starting here. No problem. So this is going to be S2. My bad. And so let's make all of these blue, shall we? Because they're nice and distinct visually. So that's where we're going to start. And then give me another direction. 5, 2, 0. Sure now. You're going to start there and you're going to move along that direction. So you're going to move along the XY plane. So we should move parallel to the XY plane here, right? So we're going to type S2 plus TD, 2, right? And this time, we've got this line. Can everyone visualize that? Fine. So we're going -10 to 10, and there you go. These are the two lines. Where do they cross? They don't cross. Fair enough. Most of the time, lines are not going to cross. Makes sense that they won't cross, right? So you're going to D2. So it is possible for lines to cross, of course it is, but it's very unlikely. It's very unlikely that two random lines in 3D are going to cross. But let's try to figure this out. When they do cross, what can I say about them? What can I definitely say about them? So easy way to do this is to come up with some sliders, right? So let me put some sliders in. So you can see 1 point on the first line and 1 point on the second line, then you can hopefully see what's going on, right? So the blue dot is the starting line, so let's slide along both lines, right? Sliders for both lines. Okay, so let me call this one T1, and I'm going to make that 0. I'm going to call this T2, and I'll make that 0. And then it's going to be S1 plus T1, D1. Cool? And then this is going to allow me to sort of slide along the line. Everyone got that? I'll make it nice and thick so you can easily see it. So make it thick, make it 10. 5 probably is enough. Okay, so that now as we slide along D1, you can see this. So let's try to like move the sliders to get them into the right place. How do you guys feel about that? All right, so let's go S2, T2, D2. So I can control these both simultaneously and independently. Cool? So let's try to move along both and try to find the closest point. So do you all agree that it's going to be somewhere around here? Yeah? So it's probably not it there. That look about right to you? Something like that. Looks about as close as I can get. Maybe the blue line back a little bit less. Something like that. Look good? What can you tell me about these points? Look carefully. Do you want the connecting point between them? I'm going to call this one P1. I'm going to call this one P2. Right? So how do you find the connecting point between two points? How do you I'm really trying to like quiz you, see how well you're understanding all of this, right? So I want someone to give me the equation that connects the two purple points. How would I figure that out? Just off the cuff. How would we do it?
P2 minus P1.
P2 minus P1 gives you the direction. So P2 minus P1 would not give you a line. That's just the direction. Do you see that? By using my STD form, where would I start? If I want to draw the line from P1 to P2, what's the starting point?
P1.
Yeah, it could be just P1. So P1 plus, yeah. Now the direction, what's the direction we said? P2 minus P1. And then times it by T. That should draw the line between them. Ah, fucking earth. Cool. You all see that? That's the line between them. And what we want to do is we want to minimize the length of that line. How do we find the length of that line? Can I call this line connector? How do I find the length of the connector? Like that, right? Why do you hate that? What? What are you talking about? What are you talking about with this? Okay, wait. Oh, no. Sorry. I'm just gonna, so this is gonna draw the whole line. How do I find the length of the line? It's just gonna be the length of P2 minus P1, isn't it? P2 minus P1, that's what I'm trying to minimize. Everyone sees that? So 1.56. So what's the shortest I could possibly get that? Well, I can just slide the sliders around and see it. So it looks like if I make that one, I get 1.55. That's too long. So it looks like 1.52 is probably the shortest I've found. 1.52. What do you notice about this line versus the lines that we've currently got?
The line that's connecting is perpendicular.
Yeah, it looks like it to me, doesn't it? So this is what I'm saying. The purple line is perpendicular to both the red line and the blue line. Now that you know that, it's going to be trivial to find it. Do you all see that? Right? So once you know that, and this is why you need the geometric intuition. Once you know the geometric intuition, it's very, very easy to solve the problem. That's why your pens are going to be your best friend in this exam. You should absolutely be playing with the pens and be like, oh yeah, I can see that they're perpendicular. Does everyone see it from this? Or is anyone confused? Right? This is the reason why people get stuck on this topic. This topic is basically impossible if you don't see it geometrically. If you see it geometrically, it's trivial. Very, very easy. Okay, so I'm going to say this. I'm going to say closest point between two lines. Everyone's cool with that? Someone scared of dogs or something? Are you scared of dogs? Oh, you love dogs? She is very scared girl. No, okay. So is this okay? So this is how we would then do it. So let's try to think of multiple ways to solve this problem. Let's think about it. So the first thing to understand is that the line R1, basically the line connecting R1 and R2 must be perpendicular to both R1 and R2. Everyone's cool with that? Anyone got a problem with that? Alright, so what I'm going to do is solve it. If you solve this problem in 3D, it's the same as solving in 2D, to be honest. It's exactly the same. So if you've got two, but obviously in 3D you have that extra dimension to play with, which makes it a little bit easier. So if I'm drawing these pictures, you have to kind of understand this is a three-dimensional picture. It's a little bit difficult to visualize, but you have to, in your head, imagine that these lines are separated. So the easiest way to draw this picture for yourself is just draw it from the top view. Okay, so draw it from the top view, orient yourself in such a way so that the two lines, so basically looking at it from Desmos, I'm always going to draw the picture in a way so that these two purple lines, these two purple points, are right on top of each other. You see that? And from there you understand that the two lines are right on top of each other but lifted vertically. Does everyone understand what I mean by that? Right, so they're lifted vertically. So this line, basically this is going to be the closest point. Closest point. To show that this one is a little bit closer, I'm going to just draw it thicker. Everyone gets that? So draw this one thicker to show that it's closer to you. Alright, so this is the closer line. Closer and further. And so the closest point is going to be this point over here, which I've done in yellow. Alright, now given this, how do we solve the problem? So you have more than enough intuition now. Let's actually go about solving the problem. So I'm going to show you two different ways to solve the problem. It's always good to see different ways. So the first one I'm going to use is the dumb person way. Okay? Dumb person way. Basically calculus. Right? So if you knew nothing, you could always solve this problem using calculus. How might we go about solving this problem using calculus? Anyone have any idea? What do you think?
R1, R2 minus R1, then minimize it.
Yeah, minimize R2, minimize. Now I'm not going to minimize R2 minus R1. I'm going to minimize instead the magnitude of R2 minus R1, but squared. Again, we understand that squaring things makes us not have to deal with square roots, and that's always nice. Okay, so I'm always going to minimize R2 minus R1 squared. Is everyone okay with this? Yep. And so I'm going to differentiate that, but then this is actually a problem with respect to what? Yeah, this is actually, how the hell do I do this? Because I've got two variables that are changing. Do you all see that? So I want you to understand it like this. So here's the value of lambda, and here's the value of mu. And both of them have a specific value. Yeah? But I hope you can all understand that there's going to be some specific value of lambda and mu where you see the minimum. Can you all kind of see that? It's going to look a little bit like that. You're looking for this point. This point. This is the point that you're after. Okay? So at this point, I want you to imagine that we took a slice of the graph this way. Yep. Do you understand that if we were to graph it this way, the graph would like look a little bit like that? It'd be like a minimal point over there. And then if we took the slice this way, same thing, there will also be a minimal point there. So this is a slice where you're changing lambda, and this is a slice where you're increasing mu, and this is going to be, you know, obviously on this axis is the distance squared. Can everyone understand that? So they both simultaneously have to be at their smallest value at the same time. Okay? But it is completely possible to do it this way, but does everyone follow how that would work? So I'm going to show you a few ways. So I'm going to show you the dumb person's way first. So let's see, how might we go about doing that? All right? So it's actually this equals this. What did you try when you tried this, by the way, Chanel?
2 weeks ago.
Sorry?
Like 2 weeks ago.
Yeah, or whenever you did it, yeah.
I don't know.
Because were you just like completely stuck? Did you have any ideas at all? Or?
And I feel like it's like a common type of question I just put in my head.
Yeah, exactly. And that's kind of why it's like it's not really something you want to be remembering, right? It's something you want to get. So this is the dumb person's way. This is a very very straightforward way. Let's get to it. How are we going to do that? What's R2 minus R1? Let's find the magnitude of R2 minus R1 squared. Okay, let's do that. That's going to be, just subtract the two from each other. So you're going to I minus 2I. So, or sorry, 2I minus I. That's just I. And then minus J minus 2J. That's minus 3J. Minus K, that's just 0. Okay? And then you're going to go plus mu plus 2I mu minus lambda. Sorry, that's a lie. That's not right. So 2I mu. 2I mu plus 2J, sorry, plus J mu plus 2K mu minus lambda I minus plus lambda J minus lambda K. Everyone's on the same page as me there? So that's ugly. And then I'm going to take the magnitude of this squared. Cool? So I'm going to group all the I's, J's, and K's together. So I'm going to get I outside of, okay, what's left here? I've got 1 plus mu squared, 1 plus mu, plus 2 mu, sorry, minus lambda. Then you got plus J, which is, what else have you got? Help me out here.
Mu plus lambda minus 3.
And then K. What have we got?
2 mu minus lambda.
2 mu minus lambda. Everyone's cool with that? And you're going to square that, and then we're going to differentiate it. Yeah? All right, so if you're finding its length squared, that's actually quite easy here. That's nice. So that's just going to be 1 plus 2 mu minus lambda squared plus mu plus lambda minus 3 squared plus 2 mu minus lambda squared. Cool?
Would it be a negative 2k in there?
Negative 2k? Where's that?
Negative 1 minus 1, so negative k minus k. R2 minus 1.
Yeah, so there's a negative 2k. Did I just destroy that, did I? Oh yeah, I did too. So negative 2k. Everyone agrees with that? Yeah, please follow along because I will make mistakes sometimes. Minus 2, right?
Yeah.
Cool. And then so this one should have a minus 2. Now, before I go any further, I want to point something out to you guys. All right, I want to point something else out to you guys. This is actually still not the best way to do it. I want to see if you guys can figure out a better way to solve this problem than what I'm about to do. So minimizing R2 minus R1 squared might actually not be the best idea. Right? Because you do want the distance squared. So this is an expression for the distance. That is true. Okay? Actually, I'm lying. This is actually a good way to do it. What am I talking about? This will work fine. Sorry, lying. So the distance squared is this. Everyone's cool with this? I'm gonna rename this to be d, if that's okay. Now to minimize it, how am I gonna do it? I want to mutually minimize both. So what am I gonna do? I'm going to find the smallest value of both of them. Now, the derivative of the first one should be what? The derivative of d with respect to lambda is what? Any ideas? What's the derivative of d with respect to lambda? What's going on? Everyone stuck? Why are we staring at the screen? If you're at the minimum point, if I change lambda, what should happen to the value of d, the distance squared? How do you usually find the minimum? What do you usually do? Right, so the derivative of d with respect to lambda should not change. So you can see here, the derivative of, this is d, I've called this d. You all agree with that? This is d, this is d, yeah? So the derivative of d with respect to lambda is 0. Can everyone see that? Derivative of d with respect to mu and lambda. Are you guys getting confused because there's two variables? Is that what's confusing you, or is something else confusing you? So if there are two variables, how do you guys think I could deal with that? So the derivative of d with respect to lambda must be 0. Okay, let's see that. That's the first condition, and you're going to solve simultaneously. Can you also see that? You got two things, two variables, two conditions. Solve them simultaneously. You'll find the answer. Can you all imagine that? So what's the derivative of d with respect to lambda? Help me. So you're going to get 2. 1 plus 2 mu minus lambda, and then multiply by minus 1, because of the chain rule, right? Plus 2 mu plus lambda minus 3, then multiply by 1, so that's easy enough. Plus 2 times 2 mu minus lambda minus 2 equal, then times by the minus 1, so that's going to be a minus. Everyone's cool with that? That should be equal to 0. That's your first condition. Pretty easy, yeah? So I'm just showing you two different ways. This is by far the more complicated way. I'm going to show you an easier way afterwards. I just want to show you that you can always solve the same problem in multiple ways, right? So what's the derivative respect to mu? Someone read that. George, give me the derivative, would you?
4 1 plus 2 mu minus lambda
Mm-hmm.
plus 2 mu minus 2 mu plus lambda minus 3 plus 4.
What did you do there? 2 mu minus lambda.
Oh, plus lambda, sorry. I've written it wrong.
Yep.
Plus 4.
Mm-hmm.
2 mu minus lambda minus 3.
Okay. Does everyone get this? Now, how might I solve these? I have two equations that need to be true at the same time. I need a value of mu and I need a value of lambda, and then I'm golden. Do you all see that? And so remember, the problem we're trying to solve is the shortest distance. So once we have mu and lambda, we could just sub back into this equation, because this tells me the distance squared, and then I would immediately know the distance. You all see that? Because this is an expression for the distance. So if I just know mu and lambda, sub back into there, I will find the minimum distance. Is everyone cool with that? Okay, let's keep going. Shall we continue? How might I solve this in the fastest possible way? What is the fastest possible way I could solve this? Would you just expand and simplify?
That middle term is the same in both.
Okay.
So if you move it to the other side, couldn't you like equate both?
You could. Yeah, you could. Can you see any other way? I don't really love that way. Why? Because then you're still ending up with a mu and lambda, right? It's no good. So the easiest way here is just expand and simplify. Expand and simplify. So expand and simplify the first one. So minus 2, minus 4 mu, plus 2 mu, plus 2 mu, plus 2 lambda, minus 6, minus 4 mu, plus 2 lambda, plus 4 equals 0. That's submission, right? All right, so let's collect all the mu's. Okay, well that's convenient. So these two go bye-bye, and then you got a minus 4 mu, and then we're going to collect all the lambdas. Why is there only... Sorry, I think I expanded that wrong. So that should be minus 4 lambda, shouldn't it? Did I expand that wrong?
Plus 2 lambda.
Plus 2 lambda, right? Isn't it?
You get minus 6 mu.
So you get minus 6 mu, right? and then I'm going to collect all the lambdas. So 2 plus 2 plus 2 plus 6 lambda. Okay, cool. And then I'm going to move all these to the other side. So 6, I got 6 minus 4. 6 plus 4, so minus 2 minus 4, so that just becomes 4. Is everyone okay with that? That's my first equation. Then I have to do the same for the other equation. So 4 plus 8 mu. This is actually the beautiful thing about extension 2 is that almost every problem can be solved in like 10 different ways. So if you, the reason I show you different ways is to really show you that getting an E4 is quite attainable in extension 2. As long as you just follow the maths, you'll get it. Just please understand though that there's usually a smart way and then there's usually a dumb way. I'm doing the dumb way first. I will always do the dumb way first. Just show you that you can always do it the dumb way, but smart way is always better, right? By the way, just before we get like super bogged down by this, right? Does everyone understand what I did when I drew this, or is this confusing to you guys? Does everyone understand what this picture is? Like, do you understand that if I graphed this, let's suppose I swap this for X and I swap this for Y. Yeah? Can you all see that these are going to make like level curves, almost like a topographic map? So one thing I kind of like to show you guys before I, shall I just solve the problem, shut the hell up first, and then I'll show you what happens when you solve the problem, because I want you to fully visualize it, fully understand what the hell is going on, and not cheapen out in any way. So let's go 4 plus 8 lambda minus 4 lambda plus 2 mu plus 2 lambda minus 6 plus 8 mu minus 4 lambda minus 8 equals 0. Okay. So mu 16, so 20 mu, and I got lambda, so minus 6 lambda, and I got minus 6, minus 8, and then 4, so I've got minus 2, minus 10, so that equals 10. Everyone's on the same page as me? Did I screw this up? Please, I want you to not be copying me. I want you to try to act as a second line of defense against me making mistakes here.
I think it might be 18 mu.
18 mu? Yeah, did you get 18 mu? Everyone else got 18 mu? I believe you. Everyone else got 18 mu? Yeah, cool. All right, so then, and the first one you got minus 6 mu plus 6 lambda, right? So I didn't screw that up. Okay, so then can we solve these simultaneously? That should be easy enough, shouldn't it? So if you do that, by the way, let me teach you a trick, because I like tricks. So minus 3 mu plus 3 lambda equals 4. I can divide those by 2 as well, right? So 9 mu minus 6 times divided by 2, that's 3 lambda equals 10. So I believe mu will just be, please check this for me, but I believe that mu will just be 4 times minus 3 minus 3 times 9, all divided by 9 minus 27. Can you just plug that into the calculator for me?
Where do you get that first?
I'll show you in a minute. The
minus 3 mu plus 3 lambda equals 4.
Equals 2, doesn't it? Does that equal 2? That should be a 2 then. 2 times minus 3 times 9, yeah, that's cool. And then minus 3, and then minus 27. Cool. What number do you get there?
11 on 6.
11 on 6 sounds good to me. And then lambda, by that logic, should be minus 3 times 10 minus 2 times 9 on 9 minus 27, which is?
Sevan, for the second equation, you didn't half the 10, unless you're not supposed to.
Thanks.
Mm.
Yeah, I was definitely supposed to. So, I just do dumb things sometimes, like it just happens. So, wait, minus 3, so let me check my math again. So it'll be 2 times minus 3, that's correct, and then 3 times 5. That should be a 5. Okay? And then that'll become minus 3 times 10, that's correct. Minus 3 times 5 this time. Sorry, I'm minus 3 times 5. And then minus 2 times 9, that's correct. And 9 minus 27 is 9, 18, 20. Yeah, cool. So what are the two numbers you got?
7 on 6 and then 11 on
Did you guys get the same when you solved it the normal way? All right, so let me teach you that trick because it's useful. Like if you're solving two simultaneous equations. Now this comes straight from the cross product. Have you guys learned the cross product before? So this instantly comes from the cross product if you know the cross product well. If you want to solve simultaneously two equations like this, look at this. It's actually cheeky as hell. So I can actually just rewrite this as minus 3, 9 times mu plus 3 minus 3 times lambda equals 2, 5. So whenever you're solving two simultaneous equations like this, see, you could write them like that, and that still is technically the same thing. Do you get that? So the trick is very, very simple. If I want to solve for mu, I'm going to just take the cross product with the vector 2, 5 everywhere. Do you sort of see that? So I'm going to take the cross product with the vector 2, 5 everywhere. So I'm going to go 2, 5 cross minus 3, 9 times mu, and then plus 3 minus 3. Sorry, I'm trying to get rid of, because I'm trying to make mu the subject. Is that cool? So if I want to make mu the subject, my bad, I'm going to just take the cross product. Remember, two vectors that are in the same direction have a cross product of 0. If you remember that, I don't know if you do. But let's say that if I want to get rid of this guy. Yep. So what I'm going to do is I'm going to take the cross product with itself. Okay? So minus 3, 9 cross 3 minus 3 lambda equals, and again, cross product changes if you do it in the wrong direction. So, you know. Okay? And so the cross product of anything with itself is 0. That's cool, so I don't even have to bother with that. And therefore lambda is just the result of basically the cross product of 3 down. Now if you remember how to do the cross product, you go this number times this number minus this number times this number. So you go minus 3 times 5 minus 2 times 9. The mechanics of doing it are actually pretty easy. I always screw up arithmetic in my head. And then the bottom number, because you're going to divide by this number, which is going to be minus 3 times minus 3. So minus 3 times minus 3, which is the 9. And then you got minus 3 times 9, which is minus 27. That's how I got that number. Pretty cool, right? So quick solve. So the basic way I do it in my head, so the way I did it in my head, you notice I did most of it in my head, is I'm going to just solve. I'm just going to take, I've got these two equations to solve, right? Got these two equations to solve. So if I know I want to solve for that mu, right? What I'm going to do is I'm going to replace the mu with a 2, 5. So I'm going to replace the mu with a 2, 5. So I'm going to go 2, 5. And then I imagine in my head 3 minus 3. And then I do the cross product there. So 2 minus 3. Minus 3 times 5. Cool. And then at the bottom, I'll just do the cross product directly. Because you notice there, it was just the direct cross product. Okay? So then I'll just do the cross product directly. So it's going to be minus 3 times minus 3, which is the 9. Then minus 27. Yeah? So you can just do that quickly if you want to. All right? So anyway, the answer is 7, 6 and 11, 6. I'm happy, 11 on 6. I'm happy with that. Now, what I want to show you is we're going to go back to Desmos and visualize this, because it's very, very important that you understand what the hell you're looking at. Otherwise, you're not going to be able to solve similar problems. All right, so, oops. Let's do this. So back here for a moment, I'm going to graph my function d. D is a function of lambda. Lambda I'm going to just call capital L, and mu I'm going to call u, because it looks like a u. Okay. Can someone read out d for me, please? D squared. So it's 1 plus 2u. Yep. Minus lambda squared.
Yeah. Plus u plus lambda.
Yep.
Minus 3 squared.
Yep.
Plus 2 mu.
Minus 2. Yep. Wait.
Still here, a plus here. That's not.
Yep.
2 mu minus lambda minus 2.
Everyone sees this? Now, can everyone see that this is just a function of two variables? Right? A function of two variables, you give me the two numbers, give me the value of L and U. So for example, if I said D, let's say I chose a point 3, 4, the distance is 61. Does everyone see that? The distance squared is 61. Cool. Say I chose a point 5, 8, 5, 9, the distance is 438. Yeah? So how about, I'm going to be very clever about this. I'm going to say, what's the minimum distance I'm trying to find, right? So the distance, LU, and I actually want it square rooted, but I'm not going to bother with that. Instead of L, I'm going to use X. Instead of U, I'm going to use Y. I'm going to say that's equal to 100, right? And this is going to show me all the points where the distance is exactly equal to 100. Distance squared is equal to 100. Let's do 100 squared to make my life easy. So it seems like nothing, really? Nothing's 100 squared? What are you talking about? Let's do 500. Something's wrong. Did we write this correctly? Can you guys double check that? Because not having any points is weird. Oh, there you go. For some reason, yeah, Desmos has this annoying thing where you have to put the constant on the left. I don't know why it does that. But anyway, these are all the different values. Do you all see that? So this is 500. This is a distance of 500. So let's say the actual distance, and then I can get a slider, right? From 0 to, we know it's less than 500, so let's see this. So let's see. These are all the points with all the different distances. You see this? With all the different distances. So if I make the distances maybe 2, 3, 4, 5, 6, or let's start from 1 to 100, yeah? Everyone's cool with that? I'm going to show you all the places. Where's the minimum distance going to be? You want to guess? What was the answer again? So again, these are all the distances that are 1 away. So these are the people that are 1 away. There's no such thing as 1 away. 2 away, no such thing. 3 away, those are all the people that are 3 away. Cool? 4 away, 5 away, 6 away. Do you all see how this works? Cool. And so what do you think the point right in the middle of that circle is going to be, if you had to guess? 7. Yeah, fucking oath. Isn't that cool? Cool. 6 up. 7 on 6, 11 on 6. That's not the right answer.
11 on 6, 7 on 6.
11 on 6, 7 on 6 sounds better to me, right? Right, because you have to follow lambda first, mu second. Oh, cool. You all see that? So that's pretty nice, isn't it, right? And while I'm at it, so does anyone have any problems with that? Or do you all get that? And so D is again a slider, right? And so let's go 0 to 10. And you can kind of see that these are all the points, all the various distances away. Once I slide it down, the answer should be like 2.1. But I can just figure that out by just saying, okay, let's say this is the point P, right? If I just take this point, I take the x value of this point and the y value of this point. Let's call this point the point P, or let's call M for minimum. Everyone's cool with that? D of M dot x, M dot y. That's going to be the minimum distance. It should be 4.5. Do you all see that? Everyone sees how I did that? Now, okay, we've gotten pretty abstract from the original problem now. We've kind of probably even forgotten what the original problem was at this stage. So let's go back to it. I always like to be a little bit back here. So I'm going to go back to my 3D Desmos for a moment. And can you guys actually remind me what the lines were? What were the exact... So what was the S1 and the D1 and all that? Remind me? So what was S1 again? So S1 was 1, 2, 1. And D1 is going to be, I'm just copying it from here, 1, -1, 1. Cool? So this is the first line. This red one is the first line. All got that? What do we find the t value should be? We'll figure that out in just a second. The second line is going to be 2 minus 1, and then the d value should be what? 2, 1, 2. Everyone's on the same page as that? 2, 1, 2. Cool. So these are the two lines. Those are the two lines that they asked us for. Cool. Yeah. Okay. So now what we're gonna do is we're gonna slide the sliders to find the minimum. Cool. Well, what are the sliders going to be at?
7 on 6,
Yeah, 7 on 6, 11 on 6. 7 on 6, 11 on 6. Cool. So obviously we've got them backwards there, so that's going to be 11 on 6, 7 on 6. Fucking oath. Isn't that crazy? That's very nice, isn't it? So this is a cool thing about mathematics. You take one problem that you had, turn it into another problem, which is basically find the bottom of that hill. Yeah? And then finding the bottom of the hill solves the original problem for you. This is kind of, I told you, this is the Talon mathematics. This is the whole idea. So if you can take one problem, turn it into another easier problem, that's much, much nicer. So everyone's cool with that? Okay? So obviously this is a hard way to solve the problem, but does everyone... So please tell me if this is confusing. What parts did I lose you on? What parts confused you? How do you feel about that? And the distance is going to be 2.12. Can you all see that? It says it right there. The minimum distance is 2.12. It's right there. Cool? So it's going to be 2.12. Can you just plug in the values into the original, and you should see that it is 2.12. Okay? Anyone have any problems with this at all? Or are you guys all cool? Yep. So if you just plugged in over here, yeah, this is the thing. Now, after all this work, I'm going to tell you this was the dumb way, right? After all this work, I'm going to tell you this was the dumb way. Shall I show you the easy way then? Right? So does anyone know of a different way to solve this? Projections is a good idea. Yep. Even easier than projections? Dot product. You just use the dot product directly. So that was the hard way. This was the hard way. But I hope you all agree that it wasn't that hard. Like if that showed up on your exam and, you know, it was worth 3 marks, it'd be, you know, reasonably near the end of the paper. It'd be worth it even to do it this way, even if you didn't know what else to do. So sometimes just having a hunch and following it all the way through, as long as you do follow it all the way through, you will get the answer every time, okay? Unless you fuck it up, which, you know, I have a tendency to do. But the easy way is much better, okay? So what's going to happen here? Now the easy way is to use the geometric intuition. The geometric intuition is that the line across, so basically I'm going to draw it from a different angle here, right? So what we're saying is geometrically, this line over here, which we know has the direction P2 minus P1, the geometric intuition, P2 minus P1, yep, is going to be perpendicular to the D of the first one. Yep, and the D of the second one. Everyone follows that? So what we're saying is P2 minus P1 dot D1 should be equal to what? 0. And then same thing, but for D2. Everyone's on the same page as me there? Anybody got any problems? Okay, remind me, P1 is S1 plus TD1, right? We called this one lambda, didn't we? So for the first line, it was lambda. So instead of T, they're using lambda D1. Everyone's cool with that? And P2 is equal to S2 plus plus mu D2. You'll see, like, using geometric intuition is just generally more elegant and will just generally lead you to the answer much more quickly. You're not going to be wasting any of your time there, okay? So if that's going to be the case, what do? How do we solve this? Sub them in and solve. You see that? So that's all you do. You sub in and solve. Sub and solve. And you're going to notice that it's going to be very similar, but, you know, a little bit simpler. By the way, reminding ourselves that the distance we're looking for, what's the distance we're trying to find? We're trying to find P2 minus P1 dot P2 minus P1. What we're trying to solve. We want D, which in this case can be expressed as the square root of this. Don't we? Do we know that or not? Yeah? So that's what we're trying to find. So how are we going to solve that in the easiest possible way? What can we do? Anything we can do? So P2 minus P1 dot D, and then P2 minus P1 dot D2, we just want to find those two. And then once we've done it, we're kind of golden. We're good, right? So we're trying to solve for this. So see if you can find a really, really easy way to solve it, but I think this is just generally going to be, from here, just plug and chug. So S2 minus S1, okay, minus plus mu D2 minus lambda D1, yeah, all dot D1, okay. Now, D2 and D1 are not perpendicular to each other, are they? We don't really know anything about them, yeah? But we can solve these pretty easily. So S2 dot D1 minus S1 dot D1 plus mu D2 dot D1 minus lambda D1 dot D1 should equal 0. Okay, that's my first equation. Cool? And then the second equation is all the same. The only difference is that all the D1s change into D2s. Okay? So these D1s are just all going to become D2s. How do I solve this efficiently? Again, remembering that these guys are just constants, yeah? So this guy just ends up over here, but in the opposite order. These are the constants, yeah? And these guys are also constants. We all happy with that? Say bye-bye to these guys. All right, how do I solve this quickly? Hope you see it. What have you got? You just got a bunch of constants here. So if I want to solve for mu quickly, what did we say? You can use vectors to solve the vector equation, right? So you know we were talking about the cross product before, right? So if you wanted to find mu quickly, well, mu is just going to be equal to, just using what we just did before, it's going to be, again, remember the whole idea is you take this whole thing, yeah, and then you just sort of plop it, you plop it here instead, yeah? That's the whole idea. So you're going to get S1 dot D1 minus S2 dot D1, okay, multiplied by minus D1 dot D2, okay, minus, it's going to be plus there, D1 dot D1, all multiplied by S1 dot D2 minus S2 dot D2, okay? Bit ugly to evaluate, but it's just a bunch of dot products. It's not too hard, right? And then over and the other part, you're going to get D2 dot D1 times D1 dot D2, cool, minus, or plus, this should be a minus there, and then plus D1 dot D1 times D2 dot D2, and that should be mu. Alright, bit ugly, but you can just sort of solve that. So then you just have to compute a bunch of dot products, which is a bit annoying, but that's kind of is what it is at that point, right? Anything we can do to simplify it? I don't think so. Is there? I think you're just going to have to compute all of that. I don't think there's an easy way. No? But you do know that, like, because again, this whole thing, see, this whole thing is a constant. So probably what would have been easier than doing all of this, you know, like, because it's going to come up really ugly. I wouldn't actually do this if I was you. This is probably the point where I would actually just compute the thing. So this is ugly. I'm not going to do that. It's too ugly. So what I'm going to do is I'm going to compute S1.d1 minus S2.d2 and then just rewrite these as two simple equations to solve, right? It's probably easier. So what's d2.d1? What's d2.d1? What do you get there?
3.
Yeah, sounds about right, sure. So you get 3. So you're going to get 3 mu. And then I got a minus 3 lambda at the bottom. What's d1.d1?
3.
Also 3. Nice. And d2.d2?
9.
Yep. Put a 9 down there. Hey, do these look familiar? You bet your ass they do. Look at those. See that? You're just back to the same place. Cool? So,
Lambda, that's a V.
sorry?
The last option is V lambda, that's V.
What are you talking about? Oh, sorry. But yeah, everyone sees what I'm saying? And so obviously this will come out if I'm going to compute that, will be minus 2 and minus 5. Cool? Because the signs are backwards. See what I mean? No, sorry, this one will just be 5. Yep, but you can compute that to verify. Let's do that. So S1.d1 minus S2.d2. So what's S1.d1? So it's S1.d1. What's this? 6. And then S2.d2?
-2.
Is it minus 2? 2, 3, 2. Isn't it just 2?
Yeah, plus
Ah, sure. So minus 2? What does that give you? Doesn't that give you 4? Are you sure the first one's 6? S1.d1. Oh, sorry, I think I screwed that up. That's S1. That's D1. Everyone agrees with that? S1.d1. So what's this one? Sorry, what's the dot product of these two?
0.
0. And then this one, and then we said S2 dot D1. Yep. S2 dot D1. That's
2.
2. So minus 2, and that's what we got. See? So Good. And then we're back to the same problem, and you just solve it the same way. Cool. Any problems there? We all on the same page? Cool. So that's how you would solve this problem. So either way, you can either use calculus if you like, or you can use just vector geometry. The vector geometry way is going to be nicer, but it's not much nicer. You see, like actually it's a fair bit nicer. it's a lot less work, but you can kind of see that you just get to the same place. You should get to the same place. You will always get those same equations to solve, otherwise you screwed it up. Cool? So I've been very thorough there. Does anyone, so again, what did we learn? Always the most important part, what did we learn? Hopefully a lot there. So help me out. What are all the things we sort of picked up on during this sort of exposition here? So first off, number one, I'm going to say, you can solve any vector problem using calculus. That's nice. So most vector problems can be solved with calculus. Vector problems are solvable with calculus. You probably haven't seen that before. Have you seen this situation where you're minimizing two variables at the same time before? Have you guys ever seen that before? So here you can minimize more than one variable at a time. More than one variable at a time. Okie dokie. By the way, this technique, this minimizing more than one variable at a time, this is the primary technique that they use to train ChatGPT, by the way. So this whole idea is, if you ever do learn about it, the whole idea is that you end up with a very big multi-dimensional landscape, and the idea is to like find the lowest point in that landscape. So it is pretty much the exact same mathematics that they use to train ChatGPT. It's just they do it in like a million dimensions instead of two, but it's the same maths. You just do them one at a time, and then you just minimize them all at the same time. So that's kind of how they manage to train it. The only idea is to like, how do you encode the problem? Like, you've got some problem that you're trying to solve, find the closest point. Somehow you have to find a way to write this distance function, and that's kind of the whole idea of ChatGPT. Is like, how do I encode how good a response is, and that's really the whole idea. So that's one thing. What else can we do? Another one is we can use the vector products, vector dot products for geometry. Another piece of learning here is use your pens. Please use your pens, because if you used your pens and you realize that they were perpendicular, problem was very easy to solve. Okay, use your pens. Next solution, next thing as well, STD form, right? Hopefully STD form makes some sense to you. Can you see why I prefer kind of using STD form than the whole lambda crap that they use at school? Because it's not very indicative, the lambda stuff. And thinking of this as like two cars driving at different times is much cleaner. It's much simpler to visualize it as a car moving down a road. It's a one-dimensional projectile. That's really the idea. Okay. By the way, one funny thing here is if you integrated this, what would you get? So let's go f of t. Here's another thing sort of just popping out here. Let's say I'm gonna call this a. Let's not call it a. Let's call it m plus t n. I just want to show you something. F of t. Integrate that with respect to time. What am I gonna get? What? Mm-hmm. Plus some constant, some starting constant. Is that cool? So some starting constant. Okay. So if I made that u, t, I made that a, and I made that x naught. That's funny. That's a thing. Cool. Comes straight there, right? So because it's, again, this is constant velocity. Constant velocity. If you integrate it, it becomes constant acceleration. You see that? So yeah, just fun little fact. So that's where that formula has always come from, by the way. So it's just the direct integral of that. So anyway, it is, yeah, sure. But it would be displacement, but also it would be the same thing as if you then treated that function as your position, that would also be a constant acceleration. Because then if you differentiate it twice, think about it, if you differentiate this once, what are you going to get? Well, you're going to get back to that, which is just ut plus, you know? And then if you differentiate again, you get a constant, which is going to be the acceleration. You know what I'm saying? So if you differentiate this first time, this become just at, differentiate it again, it just becomes a. And these terms will go away. You'll find on that. And so this all works with vectors. Keep in mind, so calculus does work perfectly with vectors. See? This is all vector maths. So calculus works with vectors. What else did we learn? Calculus works with vectors. Anything else? I mean, hopefully there was there's quite a few here. I've tattooed the page. I'm not going to go through any more, but I hope you get the idea. Okay. This last one. We'll write this last one. This one is called Cramer's rule. Cramer's rule. Basically, solve simultaneous fast. Okay. So it's also useful if you want to use that. That's perfectly okay. So yeah, lots of learning. Bless you. Lots of learning from this one. Let's do this one now, okay? Everyone cool with that? So prove that for any integer greater than 1, there's only one prime factorization. When you see anything like this, where it's like super random like this, did you give this a crack? You're just like, oh, I don't know what the hell to do? Okay, so whenever you see something that's like super open-ended like this, immediately reach for your default tool, which is going to be contradiction, right? Default tool will be contradiction. So if it's like, hey, how the hell am I going to prove this? You're going to need to reach for some kind of contradiction, right? So, for any integer greater than 1, prove that there's only one prime factor. My immediate idea, now you can do this in a whole bunch of different ways. Contradiction is not going to be the only way. There is another way which is much, much, much nicer, but I'm going to show you contradiction because it's going to be the easy way. Right, so I'm going to start with the easy way this time. The hard way is actually probably too hard for me to teach you because it'll take up the rest of the lesson. So I'm not going to do that, okay? Sorry, the easy way is going to take up the rest of the lesson, so I'm going to have to teach you the hard way, which is contradiction, which is not so hard. Okay, so easy way will uses this thing called the Euler-Totient function. Euler-Totient function. If you are the kind of kid that does the extension questions in the Cambridge book, you probably would have seen it before. It's that one, which just counts how many prime factors there are less than a specific number x. Okay, so there was a question on that in Cambridge somewhere, but that's the easy way. But it's going to take me too long to teach that to you, so I'm going to do the hard way instead. Hard way is contradiction. Okay, so anytime you have an open-ended question like this, I'm going to reach for contradiction. So what I'm going to do, step 1, I'm going to assume it's false. Right? Assume the opposite is true. Okie dokie. So assume you've got some number, p, some number n, sorry, which can be factorized into, so any integer greater than 1, that there's only one prime factorization. Is everyone cool with that? There's only one prime factorization. So I'm going to assume the opposite is true. What is the opposite going to be of this?
More than 1.
Yeah, there's more than one prime factorization. So that means n could be equal to p1, p2, p3, up to pn, pk, however many prime factors there are. Okay? And then there's a different prime factorization. So this would be equal to, let's call it, these are primes. So let me call it, Q1, Q2, Q3, Q4, all the way up to Q. K doesn't necessarily have to be the same as this side. What's wrong?
What actually is a prime factorization? I have a question.
Ah, okay. Sorry, I just assumed that this one was something you knew already. So what does it mean to do a prime factorization? Okay, so let's take, and this is something that you would have learned in year 8, but they don't teach you so well in year 8, right? So the whole idea is, let's take a random number, pick a giant number, 5-digit number for me, Janelle. 67. Do you think that's prime? How would we check if it's prime? How would we check if this number is prime?
Divide by random numbers.
Yeah, divide by random numbers. That's not a very good method. That's not a good method. It kind of works, but it's not a very good method. So let's think about this, right? First off, let's. Do you agree that it should be possible? Suppose that let's say f was a factor of this number, right? So f is some number that you can divide it by. Then there will be another number. So or let's say it like this, using our polynomial terms. If you've got some quotient and you've got some divisor and some remainder, if the remainder is 0, right? If the remainder is 0, then there's going to be some quotient and some divisor that I could find. Everyone agrees with that? Yeah? So first off, I would say that if I increase the quotient, what does that imply that will happen to the divisor? The divisor must decrease, right? Because if I'm going to multiply them by each other, they're going to have to make this up. So another way to say it is that 12,467 should be like a rectangle. Imagine there are 12,467 blocks in there. Yeah? There's going to be some number q and some number d that fit nicely into that block. Do you all agree with that? Now, if I increase the size of q, then d must decrease. There's no way to avoid that. Everyone is on the same page there? So by that logic, I don't need to test every number up to 12,467. I only need to test up to the square root of 12,467. Do you all see that? So if one of them is small, then the other one must be bigger than the square root. The square root is exactly in the middle. Do you see that? So the square root of 12,467 times 12,467, this is the square. Do you all get that? Let me call this one P, and then I'm going to call this one Q. So this over here, if this was the square root of 12467, and this is the square root of 12467, if I made this one smaller, let's go smaller than the square root, then this one must blow out because the area must stay the same. The area must stay at 12467. Everyone gets that? So the rule here, is to only test to square root. Only test till the square root of 12467, what is the square root of 12467, if you could, please? 111.6. So 111, there's not that many primes less than 100. Do you all see that? It's actually pretty easy to test up to 111.6. Do you all see that? So, okay, what are all the prime numbers? 2, that's 1, yeah? 3, 5, 7, I believe the next one's 11, 13. The primes become sparser as you get larger, right? So 2, 3, 5, 7, 11, 13. Would be very unlucky if you picked a number that isn't divisible by any of these. So if we check all the numbers up to 111, I'm just going to be lazy and say primes up to 111, you know, there's not going to be that many of them. 5, 7, 11, put them in a row, because I can't be bothered. So there's a fair few of them, 13, 17, 19, 23, 29, 31, and so on. Okay, can you test the first few numbers there? Can you just, let's try to break that down. 12, 4, 6, 7, let's just test those, see if it's divisible by any of those.
Seven.
Huh? It is divisible by 7. So it's going to be 7 times what?
1781.
1781. 1781. This is even better because now we only have to test up the square root of 1781. Do you all see that? So what's the square root of 1781? 42. So now that's easier. So keep going. So there's no point checking 7 anymore because the original wasn't divisible by 7. So what else is it divisible by? 13. Beautiful. Now what are we left with? What's left after you divide 7 times 13? 1, 2, 4, 6, 7 divided by 7 and 13. Yes. What is it?
137.
137. So now we only need to test up to the square root of 137, which is 11.7. So what else do you reckon? What other primes is it going to be divisible by? 137 has to be divisible by something else, doesn't it? No? So what does that tell you? 137 is a prime number. You'll see that? And if I give me the next 20 primes, 137 is in fact a prime. Very good. So this is the prime factorization for this number. Prime factorization. And the point is that it's unique. Does that make sense to everybody? This is the unique way to write 1, 2, 4, 6, 7 in terms of primes. Do you all see that? So then we're going to ask the question then, what other factors can the primes take? Well, what other factors can it take? So examples, let's look at some prime factorizations. So one of the examples would be, let's say 2 to the power of 6, 3 to the power of 2, and then 17 squared, and then 29. Is that cool? So actually, let me do this. I'm going to get you to do one instead. So we're going to do one more. I just want to show you that they can be a lot more interesting than this. Right? 2 to Okay, let's do a big one. 8485171. 848517112. There's an ugly one. All right, can you help me with the prime factorization, please? Let's figure it out.
I can take out 2 already.
Yeah, so I could take out 2. But the question is, how many times can I take out 2? So how many times can you divide by 2? Keep dividing by 2 until you can't anymore. And count how many times, yeah? Ten times? I don't think so. Double check that.
I got 10 as well.
848517112. Ah, whoops. I may have fucked up, folks. Sorry, I wrote the number wrong. Thanks for catching that. Sorry, that number was way too small. Can try again. So let's try 7233608 That's the number I wanted. Sorry, my bad. $7,200,000,000, etc. 8 times. 2 to the power of 8. How many times can I do 3? You just take that number divided by 2 to the power of 8, and then you continue from there, yeah?
5.
So 3 5s, I agree with that. And then could I do any 7s? Any 11s? Any 13s?
2 11s.
2 11s. And then any 13s? No. 17s? What's left? What are you left with?
961.
961. So you're gonna have to check all the things up to the square root of 961. Yeah. What is the square root of 961?
31.
Oh, that's a nice number. Which means
31.
also is a prime. Yeah. 31 squared. That's it. See that? Every single number in the world can be factorized in terms of a certain number of primes. Is everyone on the same page here? So does this answer your question now? Yep. So you hopefully understand. So that's our first little learning, is that prime factorization. Prime factorization. Because you can't prove something if you don't know what it means, right? Now, what I've shown you here is I've assumed that it's unique. You know, I haven't. But notice we've tested it for a few numbers, and you know, there's no other. The process we generated the prime factorization by kind of implies automatically that there's only one answer. You know what I'm saying? Because if there, let's think about it. If that 2 to the 8 was not that 2 cannot be divided by the 3. None of these can be divided by any of the others. That's what it means to be prime. Do you all see that? So here's the thing. Okay, so now we're going to assume the opposite is true. We're going to assume that P1 times P2 up to Pk is equal to Q1, Q2, Q3, Q4 up to Qj. Or let's do I and j. Okay?
What is that?
What is what?
What does that mean?
So think about it. This is the prime factorization. This number n that we had, yeah, can be factorized in terms of these primes.
Q
Okay.
is also prime number?
Yeah. Yeah, P and Q are both primes. So for every Pi and Qj is prime. Do you understand that? Everyone's on the same page as me? Now,
So P's one set of prime and Q's the other. Is that what it is?
yeah, everyone's on the same page as me there? So, now if this is going to be the case, this number over here is going to be divisor 1. And this number over here is going to be divisor 2. Cool? Now, P1 and Q1, you could say you could find P1 by saying n divided by D1 equals P1. Yeah? And n divided by Q1 is equal to D2. Is that cool? Maybe I should call this capital D, 1, just so that we can make it super clear. Yeah, divisor 1. Yeah, but the whole idea is that both P1 and D1 have to be basically n on D1. They have to be. Can they be simplified? N divided by D1 should be equal to P1, shouldn't it? They should be the prime. Yeah, and then n divided by Q1, that should also be the prime. That should be another prime. So then, what I've got here is I've got. Oh wait, have I written this right? Sorry, I haven't written this right. Divided by divisor 1 should be Q1. Is that okay with everybody? Yeah. So what we're trying to show is that is there a contradiction here? So we're saying Pi, for every Pi and Pj, they're unique. Is that cool? There's no value. We're not saying that no individual value here cannot be here. We're saying that the net values can't be the same. Is that cool? Does it? Yeah, so they multiply to the same number, but they're also all prime. Does everyone follow that? So all of P1 up to P3. I think this method I'm following might not be the best way to show it. There's probably going to be an easier way. But do you all sort of see that? Like P1, P2, P3 all the way up to Pi, and then Q1, Q2 all the way to Qj. These two should be different sets of numbers. Like, for example, if I did this one, sometimes you have to sort of just like refer back to a problem, yeah? So basically, this one over here would be 2 times 2 times 2 times 2, 8 times, and then 3 times 3 times 3, 5 times, and so on. I'm not saying that you can't have a 2 here and you can't have a 2 here. We're not saying that, right? But what we are saying is that you should be able to divide one by the other, and then you should end up with a factor. So I'm just trying to think, is there probably an easier way to prove this? And I'm just realized that there probably is. There's actually a much nicer way, right? So there's a much nicer way. But let's think about this. How can I prove that this? I've thought of a nicer way, but then let's say, suppose this could be written in a different way, right? So because what are all the prime numbers? You got 2, 3, 5, 7, etc. Yeah. The primes can be listed in a specific order. Everyone agrees with that too? So we can always rewrite them as 2 to the, so we're saying that there should be a different number, 2 to the A times 3 to the B times etc. Do you all kind of see that? Yeah. All right. So let's use that. Let's use that fact, and I'm going to write it a little bit differently. So these primes are in the same order, but let's write it in a different order. Let's see this. So these are all the primes in order. So prime 1, prime 2, prime 3, all the way up to whatever. And I'm going to write that as same prime 1, prime 2, prime 3, all the way up to any other order. I, J. Well, you can just go up to infinity, really. You don't even need to stop. You can go up to infinity because you can include all the primes here. What we're saying is that the indexes must be different. Do you all see that? So P1 is 2, P1 is, and then 3, and so on. So if I want to be very clear, just so that no one's confused at all, the first prime is 2, yep. The second prime is 3. The next prime is 5, and so on. Everyone got that? Then you got 2 times 3 times 5, and I can literally be explicit here. Now I can call this, this is the first factorization, A1, A2, A3, factorization 1, and then factorization 2, B1, B2, B3, and so on. Cool? Everyone's on the same page there. Yep. But what I'm saying is that these two numbers, these two, this one and this one, have to be different. Do you get that? So once I multiply them all out, they're different. But here's the thing. What can you tell me about this? So let's say that are divided by 2 to the power of A1. Let's suppose I divided by 2 to the power of A1. That should hopefully make it very clear to you. What's going to happen? So if n is equal to 2 to the power of A1, and then I don't care about the other terms, so let me just call them divisor 1. Yep. And n can also be written as 2 to the power of B1, and let's call that D1. Let's call that D1. After this question, we'll probably take a little bit of a break, huh? We've been pumping too hard. Yep. So everyone's cool with this so far? N equals 2 to the power of A1, which is D1, and then n equals 2 to the power of B1 times D1. What can I do here? Should be straightforward. What can you tell me? How can I prove that this leads to a contradiction? How can I prove that A1 and B1 can't be different? No? You could, yeah, you could equate them, or I'm going to just be simpler. I'm going to actually divide by 2 to the power of A1. Divide by 2 to the power of A1. Yep. How does that help me? Yep. So if I divide it by 2 to the power of a1, this number, what can I say for sure about this number? It is definitely an integer. Everyone agrees that? Has to be an integer. Yeah? What can I say about this number? Definitely an integer. Cool? Okay, now what? Well, I can break this up. Now, if this is going to be an integer, I need this to be an integer. I need this to be an integer because I've already proven that it's an integer. But this is only an integer when b1 equals a1. So only or b1 is greater than a1. Only an integer if b1 equals b1 is greater than a1. Everyone understands that? Everyone is cool. Yes?
What if it's equal to?
That's fine. Still an integer, because 2 divided by if they're equal, then we divide, right? So b1 is equal to b1 is greater than or equal to a1. Is that cool? Everyone's on the same page. What do you think I'm going to do to finish this off then? So I've proven that if you divide by a1, b1 has to be greater than a1, greater than or equal to a1. What else can I do? Yeah, divide by b1. And then I'm going to get the same problem, right? So I'm going to do, if I did n divided by 2 to the b1 this time, yep, this is going to be 2 to the a1 d1 all over 2 to the b1, same problem. So I'm going to put the d1 over here. And then, okay, this is definitely an integer because it was a prime factor. This is definitely an integer because it was a divisor, whole number divisor. This is only an integer if
a1 greater or equal to b1. So the only places that overlap is a1 equal b1.
a1 equals b1, which is a contradiction. Contradicts my original statement. Do you see that? So again, you need to practice this a fair bit to really understand how to do this. But notice that if I look up the solution, it's going to be different to what I just told you. I'm almost certain it's going to be different to what I just told you because I just used the facts. I sort of played with the numbers first, and then I went, okay, what's happening here? Right? What's happening here? I go, oh, okay, I can prove this just by showing that these two must be the same. These two must be the same, and so on. Do you all sort of see that? And the trick you're pretty much always going to use here is just being like, okay, if one of them is an integer, then the other one must be not an integer or whatever. Okay, so basically, which set do they belong to? So this is a very common trick. So again, what do we learn here? Use set membership all the time, please, right? So set membership is pretty much the main technique you're going to use to prove all these things, including contradictions, especially contradictions, right? Use set membership to prove it. So try to prove that one of them has to be in a different set to the other one. Is that cool? That's what you're going to do all the time. Next thing I really want you to, if you're going to get good at proofs, play with the numbers before you try to prove the general result. All right? That's always what I do. So play with the problem before your proof. Problem before proof. Your proof. And, there's another piece of advice that's a little bit hidden here. Okay? Number 3, do a lot of problems. Because if you do a lot of problems, you're going to see we're going to be rinsing and repeating the same solution every single time. You're going to see that they're actually just, this is a really easy topic once you've done enough practice because it's just the same solution every time. Oh, this is an integer and this can't be an integer and so on, right? So just please do lots of problems. Lots of problems because the sort of me knowing what to do there kind of came from the fact that I've solved these problems hundreds of times before. Otherwise, I would not have known what the hell to do. Did you post the solution to this one, Chanel? Where was it? How long have we been going now? About an hour, a bit over an hour and a half, right? Yeah, cool. No. Yeah, okay. Oh, cool. So they did my first way. See what they did? Okay, let's have a look at what they did. So assume that they're prime factors. So where pi are the prime factors and qi are the prime factors. So they've said that they're equal to each other, right? Then then one of qi must be pi. So similarly, p2 equals q2. Okay, I don't like that proof. It's disgusting. Okay, but that seems too magical. So what they're saying is that they're equal to each other, right? So both sides are divisible and they're all prime, then one of qi must be p1. Okay, because what they're saying, if this is equal to this, right? If these two numbers are this, then if you divide by p1, right? This is going to be, and they haven't, this, I wouldn't be giving this 3 marks, to be honest. This is a disgusting answer. This, basically, the remainder is a integer. Is that cool? So it's divisible. And so therefore, this is an integer. Okay? So therefore, one of the factors, or some combination of the factors, is equal to p1. But that's not even, like, what they're saying here, that they're saying one of qi must be pi. That's false. That's actually a false statement. So whoever the hell wrote this solution is kind of wrong, right? Because it's not true. Like, I could have q2 times q5 times q11 multiplying to give me p1. So that's not, their proof is shit. Like, throw it out. That's actually bad proof. Okay? And this is kind of one of the problems a lot of the times, that the answers are not very good. So this is one of the problems. So if you do get a bad answer like this, I have a recommendation for you. ChatGPT is going to give you a better answer most of the time. So let me show you this. Prove that for any integer. Use Gemini. Gemini is actually a bit better at maths. Okay, so prove that for any integer greater than 1, there is only one prime factorization. Okay, so if you do this, they'll give you a proof. They'll probably just copy it from Stack Overflow, to be honest. And another really good way to do this, by the way, is, I'll show you, is to use Stack Overflow. So if you just literally paste the problem into Google, most of these problems, because they're so common, they're so common, they're doing it through an induction. Right, so you can see that they're doing it. So they're going to do it base case, and then they used induction. Fair enough? So case A, K is prime number, case B, K is a composite number. Is that fair? So they used an induction. This one over here is Euclid's lemma, which is pretty much what they did. So P1 equals PK. And then you say dividing, you have a new small integer, and yeah, so using something similar to what they said, right? Similar to what the solution said. I think, I don't know, I'm biased, but I like my solution better. What do you guys think? Which one do you find better? I don't know. Yeah, I like this one. I like this one better. Most of the time, I'm gonna try to use the fact that it belongs to a specific set to prove something. It's a lot simpler. But yeah, okay. that's how I go by it. And so the other thing is, a lot of the time, if you're not unhappy with the solution you find in the exam, that's what I was trying to show you, is just paste it into Google. So just literally Google it. So if I Google it, it's gonna give you how to do it. So you can see that it's gonna give you almost the exact same thing, Euclid's lemma and everything like that, because it's a pretty standard problem. That's how Euclid did it. So, and then if you just find it on Mathematics Stack Exchange, you might even find one of my answers on there. So, but you won't know it was me, I think. But or maybe you will. I don't know. But yeah, you'll see like different people have proven it in different ways. Okay, so some people do it induction, some people do it, you know, in general. But yeah, this is something you can always do. Is that okay with everybody? All right. So I'm gonna go make myself a tea, and I'll be right back. Is that okay? Does anyone want a tea or anything like that? Yeah, cool. All right, we'll be back in a minute. Take a bit of a break, and then we'll do extension 1. Do you guys want? Do you guys want to do any more questions in extension 2? Does anyone like strictly want a specific question answered? If there's a question that anybody posted that they want answered right now, I'm happy to do it before we go on to extension 1. Or should we go to extension 1 after the break? Yeah, I'll give you like 2 minutes, 5 minutes, whatever. Yeah, if you guys want to like walk outside, walk around, feel free to do that. Okay, we'll just be like, give you 5 minutes, and I'll be back. Okay? Anyone want anything at all? No? Okay, I'll be back in less than 5.
Cardboard cutout of Hugh Jackman. Why? How's she gonna know electric cost? Remember the cost when I give like 50 cents? How did you go around to give $10 and I keep the $10 and I just use $8? Why?
She's on a flower stuff with girl.
Yeah, how do you know?
She likes the flowers. Yeah. Oh, yeah.
What about a ring? Yeah. Is she married?
Low-key.
She's
Low-key.
She's married to our class.
How much people in our class?
Like 10, 20,
Oh,
25.
he's got what's her name on it. This is when she just said flowers and offer her in a frame in her house.
Full grooming.
Yeah, and she said that she's bought a car, a big car. And then she said Lachlan's thing about the fake degree.
Well,
Everyone
the
just
safety
buy
fruit.
flowers.
Fake degree. Fake degree about getting through our class.
Ah, a degree of getting
Yeah,
through our
because she's got
class.
our
Oh,
degree.
shit. Started orientation.
This is Lachlan's idea?
That was my
I reckon she's like, yeah.
You don't get a ring.
It's not gonna come unless we go and post
Okay.
it. Yeah.
If we find something, then I can think of it. Okay. Next week. I think it's the same, but I'm just gonna be bothered to do everything. Mm.
A very
Are we getting exams tied together? Yeah.
Why do you keep wanting a separate class?
No, because I just like having a culture. You need to work things out with the rest of
Yeah, how's that going?
finding out doing SS because of measuring like this week.
Mm.
Like exactly like that, like an actual annoying.
Hang on, wait, let me just say this one last thing to Angela.
Okay. She's honestly now. I should have done a voice message.
No. Actually, that's a good bet.
Second voice message.
Alright. I'll be Remy and you be me.
Okay, what did you say?
Like I just said, hey, do you want to talk about it?
Okay, how do you say it? Just normally, like
You
straight
act
face?
like how I would say it and then I'll say if I
Or
did it.
laughing?
I did not laugh.
Okay.
Right.
Hey, please hold.
Nah, I got a little bit more intimate.
Oh. Oh, I don't know. Okay, pretend I said it into the
Oh. No, fuck off. But he didn't smile.
Even during class, he was asking about something, I don't know what money or something, and you were like, oh, how much, how much? He didn't even look at you, he answered the question.
He answered the question, but he didn't look at me.
Yeah, exactly.
I'm not gonna let his issue be my problem, bro. I already did everything.
You are like the shittest friend ever, but like, if you
And
overlook
he's good
this,
at everybody else.
I'm sure you've done nothing to him before.
Minimum this, bro.
If anything, half of them have done more than to him than you have.
Yeah, that's good.
No,
Did
nothing
you
to
fucking
do with
lend him like $100 2 years ago or last year?
Me? Yes,
Yeah.
I gave him
Do you pay
150.
Did you pay back?
No, he's only given 100.
Seriously?
I don't, but I'm not like.
Get
This
this
is
hand
it.
off your
I already told him. I gave him 150. I said you don't need to pay me back.
You're such a
But he's charging for
unscalp.
schools.
Huh?
But he's charging for schools.
Yeah.
You should get like
No, I'm not gonna bring that up. And then last weekend he asked for 500 Robux, but I donated him 2,000 Robux instead.
Are you serious?
Yes, what it was.
Why would you?
Because I was just being nice.
You're
Is
getting
this
more
after
shit.
the class?
No, before.
So he's doing all this and he's doing.
No, but I wasn't doing it for like anything. I
Yeah,
just
but
had
you
Robux.
just
So
did it.
yeah.
I know, and then just
I
said
declined
nothing.
to go in half.
No, because then I saw how happy he got. I was like, oh, what a cute little Asian boy. But
How much did you pay Gordon for like all this shit?
for Walker Fun.
Also,
This
are
week.
you
Oh no, I
guys,
paid him 40. I paid him
are
40.
you guys willing to pitch in $38 for Nat's gift?
No.
Just $38.
Actually, I don't know if it's the same for you guys, but it should be.
$38.
Necklace from Pandora and it's not.
That's nice.
Where do you think money grows on, bro?
I don't know why he's so angry with me though.
Yeah.
Like, yeah.
Don't stress
And
about it.
Aiden as well.
No. Yeah, Aiden, I don't know either. I swear Aiden.
Like,
Aiden.
talking about like.
Nah, he's
He wants
talking
to kill
Aiden.
Tell me he wants to kill Aiden, bro.
Seriously?
Yeah, swear to God.
They
he's-
really said in business they would not speak a word to each other.
Today.
At all?
At all.
He said he can't wait to go to school to kill his donkers.
Honestly, I'm kind of worried about you guys on a school decision.
Nah, I've already spoken to like Lachlan, Gordon, and Joel. I said
Okay.
like you guys need to watch me
Why?
What
because
do
I
you
cannot
do?
defend myself. If Remy's like plotting anything against me.
Wait, were you supposed to be his cuff or could you?
Yeah,
They're not.
yeah.
We're gonna go to his car now.
Ask Heidi.
What's this for chocolate? Oh, Julian's one from. Probably him.
Who?
Okay.
Please say it.
You should know them best. Like,
Who?
you had her for the past 4
Oh,
years.
Louise.
Yeah.
Yeah, what about her?
What can we get her?
Some
Please.
beautiful earrings
Okay, from where?
from Gucci.
Well, yeah, because you can afford that.
I don't know. Where do girls get earrings from?
True. Okay, I don't know what she likes. She said she likes gold, right?
Maybe like a necklace, a
It's
bracelet,
expensive.
We
I
can
think
have a
earrings-
bracelet. She has a bracelet.
a physics bracelet, and it says "What the flux."
I think earrings are probably better because we can find nicer ones and they're less
Okay.
expensive for a budget.
Shall we put them together? Did you find it? She doesn't give me the
Crowds,
Okay, yeah.
Did you hear she accepted for a photo?
With who?
Our class
When?
on our last
Are
lesson.
you serious? Who asked her?
She's. I think Joel. He was like, "Can we get a photo on our last lesson?" She said only one photo.
Why doesn't she like photos? These are cute.
She's a cute camera shy little girl.
She gold? She's silver. Does she wear gold or silver?
Silver.
100%?
What's a bracelet?
Have you seen her pearls? They're always silver.
Yeah.
And her earrings as well.
But the pearls are white. The actual
And
earring
her-
itself, are
and
the
the
earring
necklace.
silver? Or, okay, stop.
And her beautiful blue luscious eyes.
Okay, we get it.
But I want
I can see the deep sea ocean
Please
through
stop.
her.
What else can you see on here? Huh?
Oh,
Just stop.
What
Stop.
else I can see on
know
it?
what else I can see.
What are these ones?
I can see that
Those,
big,
do you see
They
this,
take quite a while.
big juicy,
do you think that gets
beautiful
alive?
smile. Yes.
Did I enjoy
Is
the
it
blue
this
ones?
because alive?
Which
The blue ones.
silver blue pay?
Yeah, yeah. They
Oh yeah,
100%
silver
do.
blue pay.
I could see that.
And how about silver mother of P?
What if we get her a beautiful dress for formal?
A beautiful dress for formal.
Yeah.
Oh, I gotta buy this.
First of
I'm
all,
gonna
Yes.
dance with her for formal.
imagine you get the wrong size. That's
No,
insulting.
I'm
Right,
gonna
chip
go
like
exactly.
That's not.
Yeah, get really small and go off.
Store, Weather Park.
You're bro.
Get her a shirt that's like really really small and go off. Oh, I didn't know.
Trump, bro.
Well, then make her wear it.
Yeah, and just put it on and go. Oh.
Really out of control.
No, I'm not. What are we getting, Libru?
Are we doing
Flowers in the
a
car. I don't know, like, we haven't had it long enough to be like,
Because I'm doing one
Okay.
for pastoral, but if it didn't
are
work
you on
out,
the group chat? They made a group chat for you.
We're doing one for Plan B WhatsApp.
Oh, is that what come in? Is that what come in? At the
Yeah, good boy.
Well, actually, I don't know what else is in the car.
Wait, what about Hickman though? I feel like Hickman's done so much for our cohort.
Yeah, but
Hickman
it's
is gonna get
fine,
lost.
he gets- I don't
I'll
know.
give you Shalala something, I feel bad
I
now.
know.
Nah, it's like
Even if
No,
it's
like,
like
flowers.
flowers.
Hey friends, do we have any ideas for her?
Hey! Don't disrespect my girl like that.
I think Angie bought a card for the group, so we
Is yours taking a photo?
Just send it.
Show me,
show me, show me, show me, show
me.
I'll send it, bro. It's hard as you possibly
Yeah,
can.
yeah, yeah.
It's not saying whether it's
Should I send it or is that too dog?
No, you can send it, you can send it.
Okay.
Oh my god, bro actually sent
Oh
it.
my god.
Oh my god.
Did you do it yet?
No, you can leave it, you can leave it.
Why does it? Oh, yeah.
You know it. Can I
I
add?
don't think I've ever seen Tyrese snap on any group chat ever. I'm so proud of you.
Oh, I was just accusing Lauren.
What did I do?
Why did she save it? Why did she save it?
Oh my god, bro. Oh, come in, say jail, bro.
Yes, my girl's back. I'm stealing her from Remy.
You want him to hate you more?
Yeah, I'm gonna give him revenge.
I mean, it was you know,
Were you recording? Please delete it. 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 Please listen it. Please listen it. Please listen it. Please listen it. Oh my god. Oh my god.
What'd you say?
That was scary.
What do you want to do?
Wow.
I'm so sorry.
By Mr. Brady.
No, he said he wants to unsave.
Oh no, no, no.
Save the chat.
She can save that.
Okay,
She can save
well,
that.
what do you think about the group? Oh, the fuck?
You can delete that again.
I would do it.
Who's Jess?
Jessie.
Just out
Sorry,
just
we
outside
just
my
had that.
house.
Just no, just be.
Which is me.
Wait,
You
please
don't want to
message
sit
in.
next to in class.
Wait, please mention in the chat. Say welcome, just Atar.
Hi, yes, hi. But what just as I say in the grade group chat yesterday, she's
Oh,
saying
no.
she wasn't.
What did she say?
She said she told
Are you
she's not obeyed the shush. And then
Oh, is
she
that
told
it?
me,
No, but
oh, sorry, she's such a drag.
Wait, did you give me the context there?
Why didn't you message in that group
you're
chat?
reading.
I'm not in the group chat.
Oh, you're not?
Nah,
Why?
because I thought it was for senior staff or something.
But
Senior
this
assassin?
is lazy.
Someone at him right now.
No, please don't have me. It's like
Oh,
1
there's
week
more
left.
messages. I haven't opened it.
Yeah, but that's what we discussed all the.
Well, see,
creatures
just
and
Sadio-
shit.
Yeah.
Savio's getting cucked, bro. Yes, she a cuck.
What does that mean?
That's not so
Oh
loud.
wait, Lauren, do you really want to know what I mean?
No.
Come on.
Wait, Lauren, okay, I'll draw a picture of what it means.
Oh my god, definitely not. Just explain.
What a cuck. And draw a chair, draw a chair. And then just show me the illustration.
Am I gonna regret looking at this?
Probably.
They're sitting down in a chair, by the way.
What are they watching?
That they're sitting
No,
there.
I don't want to know anymore. It's fine. It's just me. Okay, here. This is where it started.
She shocked me. She shocked her.
Are you serious?
You made her cry.
Why is it under the leg?
Because she loves it.
Hey, show me, show me. What the say?
No, the video, bro. They're watching.
Peach
No.
Hey, you drew it.
No, but you want to know. You asked me, you asked me.
No, I'm going to tickle you. See what it means now?
Do you want to see
Wait,
messages?
you
No.
didn't explain it.
Well,
Do you want to see messages?
See.
6, 7.
Wait, from how long ago?
Yesterday.
Like from this message?
Yeah, no.
So you're not going to Evan's messages and tell him to shut up?
Do not. Not ongoing.
Send it
Evan.
to the senior group chat.
Don't, no, stop, don't, absolutely don't.
Well, let's say instantly, but take it.
Yes, stop.
Oh my god.
Don't even
To the senior group chat.
don't even pray for it.
Oh.
I think it actually probably got worse.
That's actually too funny.
No.
I haven't watched
The other day, I think Angelina pressed follow all,
It's like an option
where you
where
follow everyone, and it's like all the Jacob Evan.
Bro, entrance fee. Do you think someone will pay an entrance fee? Please,
What?
And
Would you guys go?
Can I press play video?
I haven't seen it yet.
doesn't
but-
say anything.
Alright, let's watch it
Yeah,
together.
put up.
Is the one apparently newly streaming.
Is that just that part?
What?
Was that from yesterday?
That is just a phone.
Wait, what is just Athar doing to her?
It's not
Give me
actually
tissue,
a phone.
please.
I don't know.
Would you guys go?
Arigato gozaimasu.
Would you guys go? Would you go?
Go away.
You think I'm a fucking joke, cunt?
To the party?
Why are you laughing at me?
She's going to grab.
Hey, you think I'm a
Oh
fucking...
yeah, when?
Just joking.
I think after we graduate.
Yeah, next week.
Sometime next
So after
week.
HSC?
No, wait, just for like 3-4 weeks before.
6, 7.
Alright. It is time to return to the matter at hand.
Would you go?
So guys,
Is it before or after HSC? More like before party before the HSC.
Yeah, it's like party. It's like
Yeah,
the whole
but
break,
still.
it's fine.
You can't celebrate
Just
before.
don't drink when you're fine.
Why would I
AFP.
celebrate before the HSC?
what are you talking about?
Just talking about going to a party.
Someone's
Why would
going
you?
to grab
Why would you go to a party before you finish HSC? There's nothing to celebrate.
Fucking hell. Alright, guys. Just before we continue our in our things, I would just like to point out, how are we all going? How are we going?
What
So-
update?
Forgot to update it. God damn.
Wait.
What?
I accidentally did English extension 2 instead of math extension 2 when I submitted it.
You're stupid. Okay, no, I'll fix it for you. Just like, but it's not a big deal, to be honest. I mean, as long as you know, it's mostly for your own tracking. So you can just put on a filter view and people will laugh at you. But because I like laughing at you, I'm gonna do it. So I'm joking. You're cool. Where the fuck is Tyre? Actually, what is your last name, bro?
Urutia.
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 What is this, bro?
That's Chilean.
Oh, Chilean. Are you Chilean?
Yeah.
Oh, my best mate when I was a kid was Chilean.
74 English thing, though. It's not bad.
The Arezos. You know the Arezos?
No.
I'm gonna go to Chile
When?
on the way to Peru
When are you going to Peru?
on the 8th of October.
Yeah.
Good luck.
Does that make you sad? Sorry, guys, but don't worry, you'll have Julian. He's great. Okay, so but is this cool?
Yeah.
When is your HC?
16 October.
Oh, okay.
It's one.
Wow, it's almost here. Fuck. Okay. So yeah, this is cool. Which one's the extension to? Oh, this one here. I can't change it here, can I? Oh, I can. What do you want me to change it to?
Physics.
Oh, I can't. Wait, maybe I can. Sure. Ah.
No, it's math extension.
Surely I can. So, Tyrese, this one here?
Yeah.
Cool. Great. Now, this is the student progress. This is total completed. This one seems to be broken for some dumbass reason. There seems to be some problems, so I'm going to fix those, don't worry. But in the meantime, so first person here. So Balake, you're at 10. Good job, Balake. How many are you going to be at next week?
14.
14? Double that. The hell? No, no. Why at 14? You gonna do only 4 this week? Come on, man. You heard of me. Do at least 1 a day. Now, do you reckon 14 is all you can? Why 14? Are you gonna be busy?
I'm still doing the English notes.
You told me about that. Okay, Mardiano. You're at 10. Where are you gonna be at? Set the bar high, Khan. Come on, guys. When you're in the middle of your classes, don't listen to your teachers. Just set a timer and get to work.
60.
Playing games.
I don't even know what a game is, guys. Sorry, what did you say?
60.
Alright, that's good. Alright, George Araha. 4. Come on, cunt. What is this shit?
Update it. Sorry.
Are you even trying to win? So what are you going for?
50.
How you gonna do 10 this week?
I'm just like, I've done more, but I just haven't put it.
Oh, you just haven't put them up.
Yeah.
Okay, so 15, I love it. Let's do it. Let's make it happen, George Araha. So Lauren Joseph, you're on it. That's pretty alright. Can make that happen. Guys, just remember you're trying to get to 100 here, yeah? You guys are pretty far away. These bars are looking too small. Alright, let's keep going, Chanel. What are you doing? What are you dealing with? You're actually doing pretty well, huh? You're at 11. Good job, Chanel. Come on, Chanel, you can do better. Alright, there you go. Tyrese, what are we dealing with? Urotia.
Yeah.
I honestly feel like there should be a click in that last name. You're like, Urotia. You know, like it's sorry, I'm racist. it's like a thing I do. I can't help it. Yeah. Anyway, racism. This is going straight to the interwebs. Please remember to make it private. Please. All right. That's good. All right. I am satisfied.
Well, I did.
Ah. Nice job, Orotia. Click, click. What is it?
I'll be at probably like 8.
Well, are you serious?
You meant 80.
Are you trying to be a
18. 18.
18, you
That's
reckon?
not what I meant. No, definitely not.
What do you reckon you'll get to?
Probably maybe. Well, it's a big week this week, so it's our final week.
Is this a final week of school?
Yeah.
What week?
No, but
What
next
day?
week is like. Yeah, next week doesn't count. So I'd say probably after this week, like the growth will be exponential for the exam completion. So I'd probably
Mhm.
say maybe roughly I'll be at 10 by the end of this week.
Okay. That's fine. I'm disappointed, but it's okay. Being honest, I'm sorry. I'm kidding. I'm kidding. It's good. All right. So
We have a lesson next week, by the way.
yeah, why not? Are we canceling it? It's just, I don't know. I won't be here Monday. Apparently, we don't have a lesson, man. You guys want to do it Tuesday?
Maybe Tuesday
We can't do
I'll be at the
Tuesday.
beach.
And Wednesday we can't do it.
Why? Why?
And she wants to do the barbecue the day.
Wait, why do I care?
Is it going?
But I have math to get to.
Question: when is Angel's barbecue over?
I think it's like 6 onwards.
Starts at 6. So
No,
Monday,
like that.
Monday, Tuesday, and Wednesday. I
Maybe
can't
like
do
5
any work.
onwards.
Exactly.
You can do it from the
Can
morning.
she just do the barbecue like after we finish electricity?
Definitely not.
All right. Here's what we'll do. We will do Thursday. Can we do Thursday, friends?
No,
But-
I can't do Thursday.
Get fucked.
Just do it
What about Friday?
Make
What
the barbecue
about
Monday.
Wednesday in the morning? Are you guys still at school?
Wednesday in the morning is good.
Wednesday in the morning I have graduation practice.
Oh.
Oh, okay.
Cause you don't need to practice to graduate. What do you mean practice to graduate? Anyway, walk down the aisle. Dude, okay, cool.
If we move it to Thursday.
So no, that's fine. Look, guys, we'll sort. Wait, so guys, just be clear. Next Monday is a no. That's what we're saying. What about question? Sunday, 9 o'clock.
Sunday
9
9 o'clock.
a.m.
Like before.
Oh, but I can't do 3 hours then. No, that can't happen. And you can't do. Why don't we just do this week sometime?
This
Yeah, like Thursday.
Thursday we can do.
I can do Thursday.
What Thursday is it? Next Thursday? Oh, this Thursday. What time?
I don't know.
So I got 3:30 to 4:30. I got my attention to Zoom, which is the last one.
Mm.
And we're gonna get library with the whole
I'm gonna be bullying
Probably
my
like 6 then.
Laura, I'm gonna be bullying my
5, maybe 5 o'clock. Do you do 5 o'clock?
You're heartless. You're cold.
It ends at 4:30.
6?
Yeah,
6. Okay, we'll sort it out. All right, we'll probably do, guys. We're probably gonna do 6 on Thursday then to make up for your grad.
6.
Yes, but we'll confirm. Anyway, for now, let's keep going.
It should be like maybe 5:30.
I don't know.
Might actually be hard, eh? Because I actually have something on before then. Might actually be hard.
6 5.
I need a bit of a buffer. That would be ideal. But I'll have to confirm this one with you. I'll confirm.
We could do Wednesday next week.
West you.
Next week.
Don't you have a barbecue Wednesday next week?
We can cancel it.
We cannot cancel it.
Bro,
But like,
you
we're
go
not
to
gonna-
you go to the barbecue, bro. Me and Ferris are gonna come to
No, definitely not.
But I feel bad making you cancel. We'll sort this out. But I think Thursday this week should be okay based on what we've discovered. So it should be okay. All right. Now haven't we done this problem before?
No.
Okay. So is there any other problem that you guys really want to do before I go on with the extension 1 stuff? Because we don't have a huge amount of time left. So maybe I could do one more if there's a specific one you guys are like, fuck, I need help.
I posted some proof, but I posted today, so I don't know. I haven't really given people a chance to do it.
Yeah, maybe leave that for Thursday.
All
All
right.
right, then I'll leave those for Thursday. Let's continue on with the extension 1. Shall we?
But I definitely won't have however many papers I said done by Thursday.
No, that's fine. We'll do that. I'll check on Monday. Be like, sup. Remind me to check everyone's paper tallies next Monday. No, I won't forget. All right, cool. So I'll be like, how many papers you guys all done? Okay, cool. By the way, shit talk is allowed. You know, like on the chat, if you see someone like slacking off, talking shit, taking a screenshot, maybe posting a meme of them. Heavily encouraged. Okay? Especially if you got funny photos. Better get the 10 cunt. I feel like there are probably so many funny photos of this guy floating around, eh? I feel like there are so many. Anyway, all right, let's continue. Let's keep going. Friends, George Oraha.
Stop, don't do that. Actually, don't.
Chanel's gonna Chanel's gonna hit you with a Hadouken. Sorry. Have you guys ever played Street Fighter? Hadouken.
What'd you say?
Anyway,
What did I say?
probability.
Stop picking lashes.
Sorry, my fault.
You're allowed to do it.
Different is-
Picking your lashes?
Yeah.
Is that a bad thing?
Just 'cause it's pulling it out.
Yeah, they're cute. Why not? All right, so we're going to talk about probability first. So we talked about the axioms. We explained that. Last week we talked about overlapping sets. We talked about Cartesian products. We hopefully are all professionals at the what are these called? These things. Binomials out there. Yeah. Do you all feel like you understood the binomial last time? So that was all fine. And so hopefully you all also understood this guy, the bell curve thing. Did you all feel okay with that by the end of last time? And so I think you guys wanted one. So last week we left a note for ourselves, being like, next time prove this, okay? And just random variables in general, okay? Random variables are probably the only part that people really screw up, I think. And so to solve random variables, or really to teach you how random variables work, I'm going to show you a very cool problem. That's my favorite way to teach random variables. So here's the problem I want you all to solve. Problem. It's a very cool problem. I love this problem. It's called the Kakaya needle problem. Okay? Has anyone heard of the Kakaya needle problem? So imagine I have a wooden floor. Okay? So I have a wooden floor. Like so. Okay? Now I don't actually care about the fact that there are planks running here. I don't actually care about these because it's just going to complicate the problem a bit more, but not so much. You can easily account for these if you want to, but we're going to ignore these. That's why I'm drawing them in grey. You know, like usually they have them in grey. Now, I want you to imagine that I take a basket full of needles and then I'm going to drop all the needles on the floor. Is that cool? And so the needles will land randomly on the floor. Some of them will cross. What is it?
I've seen this.
Oh, you've seen this problem? It's a good problem. Do you know how to solve it? Yeah, so we're going to solve it. What's wrong?
She's seen it, but can't solve it.
I've seen like a real life demonstration. I haven't seen this problem.
Where did you see the demonstration?
What's it really
I
doing?
just saw some girl drop some stuff on the sticks and she was like, oh, this percentage of this.
Oh, really? There you go.
Cool.
Yeah, there you go. So basically what I'm asking you is, given, I can give you two parameters here, the width of the needle, sorry, the length of the needle, and then the width of the planks. Okay, those are the two parameters that you can control here. Now, we're going to keep our life a little bit simple for the moment. If they were both the same, I might ask you the question, what's the probability that a needle will land on a crack? So it's a fun problem because I really like to demonstrate this with problems. So we're going to say, what's the probability that a needle will, what is the probability that a needle will touch a crack? Perfectly within the realm of HSC maths, so you know they could absolutely ask you this problem if they wanted to. So then the question would be, how the hell do you solve it? Anyone have any ideas?
Does a crack include the grey lines?
I said ignore those, yeah.
Oh, okay.
Yeah, we could, we absolutely could. It's not hard to include them, but we're not going to because it just adds extra complication. And it makes the visual less pretty.
This is L equals W.
Doesn't have to. But let's suppose L equals W. Does that help you?
But L equals W, and the only way it doesn't touch a crack is perfectly across.
No, that's not true.
Ah, it lands upright there.
It can land like this, it can land like that, it can land like that.
Yeah, I see.
Yeah, it can land like, yeah. So how in shit's name do we do this? Any ideas at all? So this is going to be the goal of today, is to solve this problem. Okay, is this cool? But in order to solve this problem, you're going to need to know a bit of background. Okay, as you would probably have guessed by now, knowing the way I'm showing you shit, right? So the background is, well, random variables. Anyone know what a random variable is? Have you guys been exposed to random variables before? All right. Remind me so far, how does probability work? So random variables. Remind me so far, we had a probability, which is a function, yeah? What's the input to the function? What's the output of the function? What goes in? What comes out? Tell me. Please tell me. What goes into a probability function? What comes out of a probability function? Lauren, help me out. What goes in? No, you don't remember? No, that's all right. George, do you remember what goes in? What goes into a probability function? Chanel? No? Nobody? Tyrese? Come on, you got this, Tyrese. Save us from ourselves, Tyrese. Okay.
A set.
A set, yes, very good. A set goes in. It's part of, so you're going to have some sample space and some subset of the sample space, potentially a subset, or a subset in general, which we call some event space, yeah? Goes into the probability function. What comes out the other side?
0 to 1.
0 to 1. A number inclusive 0 to 1. Everyone's cool with that? Now, there's a really big problem with sets, right? Is that we don't know how to do math with them. Like, what does it mean to add two, to add two sets together? I don't know. Right? That's not really a thing, right? Sets have a bunch of operations defined on them, but we have to, so a group, I think I may have mentioned this before, but a group is a set plus an operation. So let's say addition. Okay? Operation. Okay, and it has to have some rules, for example. Like, for example, you could add, sorry, I said set, but it's like an element in a set and an operation. Well, technically a set and an operation is okay. Right? So what we're saying is a group, you've probably heard of group theory before. Have you guys ever heard of group theory, the area of mathematics called group theory? Or not really? Right? So one of the ideas is that you need to sort of teach the set how to add things. Okay? Like, for example, if you had a set of colors, how do you add two colors together? Well, you mix them in a paint platter, and then you just mix them all up, and then you get a new color. Everyone's cool with that? Right? That's one way to do it, but it's not necessarily the best operation. You can set up any operation you want. The trouble is that sets, there's no really canonical or very obvious way to add them. So what we would like to do instead is be like, okay, wait, I don't want to deal with sets. Sets are a bit annoying. All right? So what I'm going to do is, we have dealt with sets before, but what I'm going to do is we're going to try something different. We're going to invent this thing called a random variable. So a random variable, what is a random variable? It doesn't take a whole set in as the input, but it takes an element from the set in as the input. We all get that? So it takes an element from the set in as the input. For example, we might take a color, and then it will give it some meaning. The only important thing about the meaning is that the color, that meaning needs to be encoded into a real number. Okay? Now, let me just sort of preface this about why the hell would I even want to do this, is that I don't like functions where the input is something I can't reason about. Like I can't easily differentiate it. I can't add it to another input. I can't do that. That's annoying, So I can't do that. So I'd like to somehow convert this set into a number somehow. And that's the whole idea of a random variable. It's a very bad name. There's nothing random about it. It's not random at all. It's just a function that takes an element of the set and gives it a number. For example, it might take a color. Yeah. And what's one thing you could tell me about every color? Like, you could look at a color and tell me it's... What could you tell me when you look at a color that you might be able to encode as a real number?
It's blue.
Huh?
It's blue.
It's blue? You could encode how much blue it has.
Okay.
Yeah, you could encode a text value. You could even encode its brightness if you wanted to. You could just tell me a number from 0 to 100, how bright it is. Is that cool? Anything you want. But let's choose brightness as an example, right? Hex is also a very good one, very, very good choice, but it's not differentiable. It's not very, it has jumps and shit. It's not super nice, okay? But you could take a color and you could encode it into a brightness. Everyone's cool with that? The brightness could go from any value you want, 0 to 1,000. Is that okay, right? Now the whole idea here is, with the random variable, now we know that we need to make sets in order to put them into a probability function, okay? So what we're going to do here is, let's say that we pick a value of, let's say, all the colors that have a brightness between, let's pick a little range here, from 500 to 800, okay? Now you understand that there's going to be a whole bunch of colors, so these are going to be all the colors that get mapped through this random variable and give you 500 to 800. Is that fair? So in other words, what we'd say, we've made this new set. This set is the value set where x is somewhere between 500 to 800. You all see that? So what we would do is we have this notation that you kind of want to see here. Curly brackets, 500 is less than x is less than 800. Okay? This is a set. And if I wanted to be very formal about what the set is, it's going to be basically, if you take the element e and you shove it into x, right? So it's all the elements, let's call it x equals capital X of that elements, such that the value of x is less than 500, less than or equal to 500, sorry, less than or equal to 500, and less than or equal to 800, okay? So it is a set. Have you all seen the set builder notation before, or not really? So the idea is, this is the result, this is the such that, this vertical bar means such that, and this is the conditions that they have to follow, all right? So what I'm saying is, when you take the element e and you put it through x, you're going to get a number out the other side, right? So let's pretend the element, let me actually be very explicit here. Let's say that this is this weird pink color that I've got. You all see this? This little splotch of pink that I've got, which is a possible color in your set of colors, yeah? And let's say that the color pink, when shoved through our little random variable, gives you a value of, I don't know, 736. Is that okay? Since that does follow this condition, it would be inside this set. Cool? So this set acts as your new event space. No problem. And then you're perfectly okay to shove that event space through the probability function. And then it will just give you a value. Is that cool? So the value here would be, you see, once it comes out of the probability function, the way we would write that is that it's going to be the probability that that you get 500 is less than x is less than or equal to 800, right? So because you got a set there, you all see that? You got here a set, and then it's being plugged into the probability, so you're going to get a number. No problem, right? This is the key idea of a random variable. Does anyone have any problems with this, or is this all very straightforward, right? So what we would like to do instead is we're like, okay, this is a pain in the ass. You know, what was the process? Remember, let's remind ourselves what the process is. One, define a random variable. Right, random variable, which in this case would be x, which again takes in elements, say the color, and gives us a value, right? So which takes a elements and then through the random variable x, maps it to a real number. Has to be a real number, otherwise it's not very useful to me, okay? There's no restrictions on the real number outside of a random variable. Be aware of that too, right? It could be anything you want. It could be 1,000,000, it could be 2, it could be 5. No problem, right? So that's going to be the first thing. Define the random variable. The second thing you're going to do is you're going to build a set. A set.
Real number be negative?
Yeah, absolutely. Whole real number, right? Any real number. Build a set where the output. In fact, sometimes you can even make it a complex number if you want to. No problems, right? It doesn't matter. You could just make it just needs to turn into a number so I can use it for stuff, right? Is that cool? So build a set where the output is, or follows some condition. Follows some condition. And then step 3 would be find the probability of that set. Okay? Find the probability. Right. Okay, wait, this is a lot of effort, right? Why would we do that? Well, let me show you. This is the kicker. So what we're then going to do is this gives us a superpower. This gives us a superpower. So I'm going to take the exact same picture and I'm going to clean it up a little bit because I don't want all this stuff. All right? Take this, clean it up a bit. So I'm going to take it here and just delete a bunch of shit. And I want you to see why we would do this. And this is the part that I think people really confuse about probability. This is why, like, I would argue 95% of your teachers don't even realize that probability has got anything to do with sets because of this thing I'm about to say. Is that we realize that we don't like this, you know, we don't like to have to do this whole weird process. Notice that the process we followed was we took a number, used that to build a set, then we used the set to give us a probability. Do you all see that? That's the thing. So it's like, this is the process. It goes back and then forward like that. It's a bit confusing, right? So what we're thinking is that wouldn't it be just nicer if we could just make another function over here which combines the probability and the random variable together and then just takes the real number takes the number that I'm interested in and just spits out what the probability of that number is. Everyone got that? So it just spits out what the probability of that number is. Got it? So in other words, if I just take out the parts that I want, I can make this P of X. What's the input to P of X? Well, what is the input to P of X? Tell me. So, Mariano, what's the input to P of X?
0 to 1,000 or whatever.
Yep, so a real number. So a real number goes in. Yep. So that's going to be the output of the random variable. Everyone gets that? And so, okay, so it's going to be, let's say in this case, 0 to 1,000. Doesn't matter what it is. So it's going to take some input, and then what's P of X going to give me?
0 to 1.
Yeah, 0 and 1. Cool. Now, 0 to 1 is a real number as well, isn't it? So what have I just done? I've converted probability from set input, set output into number input, number output. Why would that be useful? Because I can do funny shit now. Like I can find the derivative of P of X. I can, all of a sudden, I am able to find the derivative. Right? So let's say this is X and this is P, right? The whole idea here would be that P is equal to P of X outside of X. This thing is called a probability mass function. Does everyone follow that? Okay? So this over here is a number in, number out function. So now I can suddenly do a whole bunch of stuff. Like if I want to, I can differentiate it with respect to X. Everyone gets that? So I can differentiate. Which hint, hint, I'm absolutely going to need to solve that problem. Right? I'm absolutely going to need that to solve that problem, otherwise good luck. Right? That's one thing I can do. I can add it. I can add the inputs. Right? Add inputs. Which I couldn't do before, right? Like what does it mean to add things in the other stuff, right? I can find averages. It basically is a superpower, and I'm going to show you that. Now, just to make sure that you're all on the same page, what I want you to do here is I want you to construct for me the following, right? So I'm going to give you a set. I'm going to give you a set here. And inside the set, I'm going to put some letters. A, B, C, D, E, F, G, H, I, J, K, L. Okay? So take, got this one, the random variable. Now, the random variable is going to be I'm going to call it the strokes random variable. It's basically going to measure how many times, how many strokes of the pen I'm going to need in order to draw that letter. Simple enough? So for A, it would be 1. Cool? And for B, it would be, it's a bit of a boring random variable. I'm surely I can come up with something else. Letters are not that interesting, to be honest. Fuck it, let me replace the letters for shapes. Is that okay? So sorry. Alright, fucking crucify me. Okay, so let me actually name this random variable. It doesn't have to be capital X, so let's call this one E for edges. Everyone okay with that? All right. Can you guys please tell me all the outputs that produce a valid output? So this is going to count the number of edges. Everyone's cool with that? What are all the possibilities? Or even more interesting than edges would be something like the corners, for example. You could define another one if you wanted to, like edges, corners, whatever, right? Corners are probably more interesting here because give you values that you can kind of see. Let's do corners, shall we? And so what would the mass function take the form of? Like what would this function be called? What would this one be called? It's the probability under C, right? Probability given the random variable C. That's what you need to do. So it's probability, you need to put the random variable there, otherwise it makes no sense, right? That's the idea. Okay? Can you tell me all the values that C could output? Tell me. What are they all? 3? Yeah, so 1, 2, 3, 4, 5. Now let's suppose that this is a uniform set. Okay, I'm also going to take it a little bit further here. So you said 1, 2, 3, 4, 5. I'm gonna need more than that. One, 2, 3, 4, 5, 6. Okay, cool. So I can have a 3 there. Yeah? So I can have a 3. What's the probability for 3? So if I took 3 and then I shoved that in there, what am I going to get? So it's a uniform set. I've told you it's uniform probability. Just keep my life a little bit easier. Is anyone confused as hell about anything I'm saying right now? Or are you all kind of on the same page as me here? So this is going to be 0 to 1. So can anyone tell me what the probability of 3 is going to be?
One on how many in the set?
Yeah, so how many 3s do I have?
One triangle.
Only the one triangle, right? So for example, if I shove in the triangle, do you agree that the random variable spits out 3? Everyone's on the same page as me there? Cool. No dramas there. What else? Okay. What do I get? How many are in the set? 9. There's, let's call this a shape set. The size of the shape set is 9. Cool. So what's the probability here?
1 on 9.
Yeah, I agree. Is everyone on the same page? Does anyone not get that? Yep. That's how it works. So what we would say is that the probability under the random variable c of 3 is equal to 9. Everyone on the same page there? Cool. All right, so then let's do another one. What about 4?
Wait, how's it 9?
How many shapes have I got?
Isn't it 1 on 9?
That's what I wrote, isn't it? Oh, sorry, not there. Yeah, sorry, that's 1 on 9. My bad. Okay, are we on the same page there? So, okay, what about 4? Now, understand that this is the set. So, where are the 4 shapes? They're all here. You all see that? These shapes all have 4 sides. All have 4 corners. Not even that. This one too. You all see that? Yep. How would I write this set? Can someone remind me how I would write this set? So set bracket, what else would I write? What's this written as a set? How would I write it? What do you think? Lauren, give it a go. Sorry. How do I write that set?
Are you writing the shapes?
No, I'm writing it as a set. So I'm actually writing the set specifically. Anyone have any ideas?
X equals 4.
Not X here, but you're close.
C.
Capital C equals 4. Everyone gets that? That's how I would write the set. So you will see this notation in your exam, so like, make sure you get it, right? So this is a set where, what does it mean? What does C equal 4 mean? Just, can you say it in English for me, Blake? Just so we're on the same page.
4 corners.
What is it? No. How do you read that in English? The set C equals 4. What does it mean? This is the set where? The set? Not sure? All right, and let me help you out. Containing elements that do what?
Where
C of that elements is equal to 4. That's what we're saying. Everyone got that? So what goes into the random variable, to be very clear with you, is a individual shape. Yeah, an individual shape goes in, and what will come out is going to be 4. You cannot put the whole set into the random variable. You can't do that, right? So that's not what random variables do. So here you're putting an individual shape in, and you get 4. Do you all get that? If I put a different shape in, you're still going to get 4. Can you all see how that's going to work? So all these pink arrows will give you 4. And same with this one. All these arrows will go in and give you 4 as the output, yeah? Okay, so then when you put 4 through the PC, what's going to come out the other side?
4 on 9.
4 on 9. Everyone's on the same page? So this is 4 on 9. Okay? Now, if you were to put the set in, just to be very clear, if you're putting it in here, this one would go in. This is the set, C equals 4. Yeah? And what comes out the other side is still 4 on 9. So the probability of the set C equals 4 is equal to the probability of PC 4. Right? Is everyone on the same page there? Cool? I just want to make sure that you are all on the same page. So if I was to write this, PC is less than 5, what does that equal to in terms of PC?
Zero plus one plus two plus three.
Yeah, exactly. PC is 0. Is there a 0? Yeah, there is. So PC, is there a 1? Is there a 1 corner?
No.
No? Then is there a 2 corner? 3 corners?
Yeah.
There is. A 4 corner?
Yeah.
Why can you do this? Why can you just add them like this?
Axiom.
Yeah, because all of these are disjoints. Right? All of these sets are disjoints. Are you all on the same page there? That's important.
Nope, 5 is less than 5, so.
Oh, sure. Then you don't include 5. Are you on the same page there? So it's disjoint. Basically, if I wanted to, I could convert that back into P C equals 0. Yeah? And then this would be P C equals 3, right? So you need to understand that, you know, a lot of the time people just think this is just a notation thing, but it's absolutely not, because it's very different, right? Like the whole idea is that here you've got sets as inputs, and this is a completely different function to this one. They're completely different, right? And so if you don't know the difference, you're going to fuck a lot of shit up. You're going to screw a lot of things up. Are you all on the same page? Anyone have any problems so far? Okay, cool. Now, what I'm going to do is I'm going to ask you the question. If someone chose a shape at random, so here's a problem for you now, right? So problem, given the set above, if someone chose a shape at random, what is the average number of sides? Okay? At random, what is the average number of sides? So this is a very common problem, right? The average number of sides. How do we solve that? Let's solve it with a simple example, right? So let's pretend we did some actual examples. So we're going to use some data here, because you guys were asking me about sample proportions and all that kind of stuff. Suppose I took 1,000 samples. So I took 1,000 people, and I got them to go picking those shapes. Is that cool? So we're going to ask, okay, this is going to be the output of the corner, yeah? And we're going to look at the probability of that corner. Is that cool? What are the outputs? What are the possible outputs of the corner? So what did we say were all the possibilities? We said we could have 0 corners. How many? We can't have 1 or 2. But we said we can have 3 corners. What else can we have? 4 corners, 5 corners, and 6 corners. That's really all we have, yeah? Now, if there were 1,000 samples, how many do you roughly think of each one should come out? Roughly. Give me some numbers that make sense for this.
250 of each.
No, that's not right. That's not, it's very, very unlikely that it would be 250 each. I want you to give me like reasonable probabilities, yeah?
222 for 0.
Huh? Yeah, 222 for 0 sounds about right, yeah? What else? How many for 3?
111.
Okay. How did you get 111?
There's 1 triangle, there's 2, 0.
Yeah, exactly. What about 4?
444.
444. Sure. 5? 111, I believe. Yeah. And then 111. The trouble is that this doesn't add up to 1,000, so what I have to do?
Add 1 more.
Yeah, add 1 to one of them, right? Now this would be in an ideal world, but in practice it probably won't be exactly this. Everyone's cool with that? Any problems? You good? If you're confused about anything, just like feel free to ask. Or is that, what's wrong? Is there?
I'll just look at them.
Yep. So
Yeah.
these are you got very lucky with your sampling here. It's very unlikely that you come up with these exact numbers. How would we find the average number of corners? How are we going to figure that out? See, that's a question that we can now solve. Before, like with our set machinery, that was a silly question. There was no way in hell you were going to figure that out. Right? You couldn't take the average of things. But now that we have actual values, we can absolutely take the average of them. You know? So let's think about it. Does everyone agree that this is going to be 0 plus 0 plus 0 plus 0 222 times? Right? Plus 3 plus 3 plus 3 111 times? Everyone sees this? and then so on and so forth. Yeah, all divided by how many? By 1,000. That's what the average would be, right? So the usually with averages we're at corner bar. Is that cool? Yeah. So what are we going to do now? So much easier would be, how about instead I write it as 0 times 222 plus 3 times 111 plus 4 times 444 plus 5 times 111 plus 6 times 112. Everyone's cool with that? And then I can just distribute the 1,000 to each of them. Everyone sees this? What do we notice? What just happened there? What does that look like? I'm just trying to bring them to the right place. What do we see? So this is these are all the random variable outputs. These are all the possible outputs that you can have. Yeah? And then these guys are kind of like the frequencies, right? Cool. So a nice way to think about this is that C bar is kind of like the sum for I equals, across all possible i's, of Ci times the frequency of the ith item. Do you all see that? Where the frequency is like just the proportion, right? And so if I wanted the true average, what am I going to do? I'm going to take the expected value of C. We're going to call this the expected value of C. It's going to be the same thing, but I'm just going to replace the frequencies with the actual probabilities, right? So it's going to be Ci times the probability of under C of the elements, which is C, little c. Right? It's a bit confusing, but that's probability of that specific I. All right, so writing that out. Does everyone follow that? That's how you would find the average? Yeah? So do you understand how I got there? I just started with the original definition of the average, broke them into frequencies, and then that's it. So then by that logic, what's the average number of corners? Very common problem that they might ask you. How do we do it? So Tyrese, help me out. The expected value of C is what?
Like just straight the answer, or like the
Well,
process?
how do we figure it out?
So we would do 3.
What did you get when you did this, by the way? What did you did you plug this in?
Yeah.
What did you get?
3.336.
3.336. Now this is not the true answer. Do you see that? Why not? Because I sampled. Do you see that? This is not the true answer. So how would I find the true answer? I would need to go every C value times every corresponding probability. Do you all see what I'm saying? Right? So I would do 0 times what? What's the probability of 0? 2 on 9. Yeah, and then the probability of 3 times 1 on 9. And then plus the probability of 4 times. Mm-hmm. Yeah.
5 times 1 on 9 plus 6 times 1 on 9.
That's the expected value. Do you all see how that works? And do you all understand what it's doing? It's calculating the average. That's what it's doing. All right, that's what it's always been doing. Everyone's on the same page as me there, right? Now, then we have to talk a little bit about the variance. Do you guys all know what variance is? Now, okay, for a Bernoulli, let's think about it for Bernoulli, right? For a Bernoulli trial, it's actually pretty easy, right? Bernoulli, we can compute that directly. How do we compute that for a Bernoulli? Remind me what the probabilities are equal to? Now, the probability of X for X wins, does anyone remember what the probability was? We derived this last time. Suppose that there are n trials where you win K. Is that cool?
K times.
Yeah. Now the random variable would not be, you have to think about, what's the actual random variable that we're defining? You have to think about what the random variable is. So X is, what does X mean? You've won 1K times. Is that fair? That's the random variable. So like, what's the probability of 0 wins, 5 wins, 10 wins, etc., right? So then the probability of X, yeah, given the number of wins, you could say the input is K if you like. Yeah, the input is the the value k, what are you going to get? N choose k. Sorry, what did you say, Mariana?
Times x to the n.
It's going to be p to the, remember p is a constant.
Yeah.
Yep, so it's going to be p to the k times.
1 minus p to the n minus.
Yep. Is everyone on the same page there? How are we going to compute the expected value? The expected value of that random variable would be what? What are we going to do? Any ideas? What do? We take the output and multiply it by?
The input.
By the probability. Output times probability. Output times probability, do that for every value, yeah? So it's going to be the sum across all values of k, start at 0 up to n, yeah? Of what? What's the output? So again, let's define the random variable so no one is confused. I just want to make sure you're all on the same page as me here. So let's see. This is all the games. This is the set of all the games that, let's say, we talked last week about the Alligators versus the Broncos, yeah? So these are all the possible ways that the game could go down, right? So for example, you might have, let's say this is an Alligators win, and this is a Broncos win. Is that cool? So it could, let's say it's a series of 5. Series of 5. So this, the first possibility with 1, 2, 3, 4, 5. That's one possible thing in the set, right? Another possible thing in the set is this one. Yep. Another possible thing is, right? So this is not useful for me, yeah? All of these have different weights. They're all uniform. Remember, that's kind of the whole idea. They're all uniform, but not exact, sorry, no, I lied. They're not uniform. They're weighted by the probability of the Alligators and the Broncos winning. Do you all remember that? So to find out a specific one, we would say, okay, the probability of each one is going to be equal to the, p times the number of open circles, plus 1 minus p times the number of closed circles, right? So the weight of that specific element, so the probability, let's say the probability of x of the specific element is going to equal this, right? Basically, how many circles do you have, and how many closed circles do you have? Is everyone on the same page there? So that's the way the Bernoulli is going to work. So, the language of random variables makes it a little bit easier to write this. Okay, so what is the random variable? What are the outputs of the random variable that you're allowed to have here? I want to make sure that we're all on the same page here. There are only a few.
0 to 5.
0 to 5. Everyone agrees with that? 0, 1, 2, 3, 4, 5. Can you have 1.5? No, because this random variable is a discrete random variable, and you can only have specific values. Is that cool? 5 is the maximum value. This is x. Everyone's cool with that? It's going to take a specific game, and what's it going to map that one to? And so you have to decide who. So let's say A's 1, k times. Okay, so what's the value here?
3.
So A, remember, is open circle. So it's 3. Did everyone see that? So it maps to 3. So in other words, x of circle, 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 close circle is equal to 3. Notice how it takes an element in as an input and gives you a value out as the output. I really need you to fully understand this, yeah? Okay? Now, what we're going to do is we have the probability, but we chosen from now on, I'm like, screw it, I don't want the probability. I actually don't want to think about it anymore. The whole idea of random variables is I don't want to have to think about this crap anymore, right? So what I'm going to do is now I'm going to map it to the actual probability, which we know is the value from 0 to 1. Everyone is okay with that? So what I'm going to do is I'm going to ask you, what's the probability of 3 wins? What is the probability of 3 wins? Let's say that p is equal to 0.6. I'll give you that as a thing. I want you to give me the exact value. Tell me the exact value. I want to make sure you get the right answer. Otherwise, you're kind of not really getting this, right? So.
I got 0.346.
All right. Can you guys corroborate, please? Yep. Cool. So then we're good. We're all. Anyone not know how to get that value? Anyone want me to show you? 0.346, just in case sometimes I get scared saying. So 5 choose, 3 wins, yeah? And then you're gonna say P, which is gonna be 0.6, 3 wins, and then 0.4, 2 wins. And then you should go 0.346. Everyone's on the same page as me? Okay, now how do I calculate the expected value then? What do? I do 0 times the probability, plus 1 times the probability, plus 2 times the probability, up to 5. So how would I write that as a sum? So you're going to type K, N, K, P, K, 1 minus P to the N minus K. Now what do you think, if I did evaluate the sum, what should it work out to be? If I solve this, so I'm going to need to solve this. This is a little bit difficult to solve. So I'm going to do it for simple, so do it for K equals, let's just do it for K equals 4, so you can do it. Usually I would prove the result by induction, but I'm just going to do it for K equals 4. Can I do that? So let's write it explicitly. Yeah? I'm going to let Q equal 1 minus P as well, just because it's a bit annoying otherwise, yeah? So what are we going to do? So give me all the terms, please. Yep, so you're going to get 0 times, sorry, I said K, but I meant N. N equals 4. So 4, choose 0, yep, P to the 0, Q to the 4. You all agree with that? Next term. 1, 4, 1, P to the 1, Q to the 3. Cool? Plus 2, 4, 2, P2, Q2, plus 3, 4, 3, P1, Q3, plus, I am running out of space. It's a bit of an annoying one, but it's not super hard. 4, 4, 4, Q4. Everyone's on the same page there? Yep. Now this one's easy because it just goes to 0, so that's nice. Okay, so at least, yeah, a little bit easier, not much though. So equals, let's see, 4 choose 1 is, what's 4 choose 1? Just 4, isn't it? Okay.
These two terms the same.
These two?
P to the power of 1 and then P.
They're not supposed to be. So I've clearly mangled this. Good catch. So this would be 1, 2, 3, 1, and then that would be Q to the, that would be P to the 4, wouldn't it? So you have to be careful, yeah? Don't screw that up. Everyone's on the same page? So P goes 1, 2, 3, 4, and then Q goes 3, 2, 1, 0. Okay? Everyone's on the same page there? That's a bit ugly, but let's say we've got 4 P Q cubed plus, what else? What's 4 choose 2 times 2? 12. P squared Q squared. Yeah. Plus. So 3 times 4 choose 3. What's that?
18.
Huh? 12 as well. And then the last term? Just 4, isn't it? Okay. Can we simplify this? It's going to be a bit annoying, but you're going to need to do some expanding. You all got that? You're going to need to do some expanding, otherwise, like, it's not going to simplify very nicely. So what we can do to make our life just a little tiny bit easier is I'm going to write this. Okay, so I'm going to need to now write this as 1 minus p cubed plus 12p squared. And again, usually you would prove the general case with induction. I don't know if there's an easier way, but I mean, I think there is. Yeah, so you would do the first 2 or 3, and then you realize what the trend is, and then you can prove it inductively. Yeah. So that's usually the easy, but the trend is pretty easy. I think there's probably an easier way to prove this. I'm just not aware of it off the top of my head. 1 minus p plus 4p to the 4. Everyone's on the same page there? So I'm going to need to expand this out. 4p, this is going to be 1 minus 3p plus 3p squared. Am I doing this right? What was it again? So you go, yeah, minus p plus 3p squared, and then minus p cubed, yeah, plus 12p p squared, 1 minus 2p squared, minus 2p plus p squared. I'm going to just expand that, 12p cubed minus 12p to the 4 plus 4p to the 4. Yep. What do we know the result is going to be when we're done? What's the expected value of the Bernoulli again?
4p.
Yeah, it should just be 4p after all this is said and done, which is kind of crazy, right? So let's just go on a crossing spree now, shall we? Because we're lazy. So I reckon pretty much everything except the 4p should live. You see that? Everything else should die. Let's see if that's actually true. Okay, so I believe that the 12p squared will let's just expand it because you get 4p minus 12p squared plus 12p cubed minus 4p to the 4 plus 12p squared. I should have picked 3. Sorry. Minus 24p cubed plus 12p to the 4 plus 12p cubed minus 12p to the 4 plus 4p to the 4. Okay? Does everything cross out like we want? It does. That is crazy. Goodbye everything. Goodbye everybody else. You're just left with 4p. You're pretty crazy though, right? All that simplification. I'm sure there's like a easy algebraic way to do this. I just don't know it off the top of my head. But you know, if you're bothered, you'll see that here, when n is equal to 4, you get the answer 4p. And if you repeat it for 5, you get 5p and 6. So in general, generally, the expected value of x is equal to np. Everyone on the same page as me? So that's how we would do that. That's where we got that from. Nice? Anyone have any problems with that? Okay, cool. So then the last thing to talk about then is the variance. Okay, so the last thing to talk about is the variance. So what the hell is the variance? All right, variance is actually very easy to prove if you know the expected value, which is very nice, right? If you know the expected value, then variance is quite easy to prove. Anyone know what variance is, or not really? Can you give me a good explanation of what the variance is? So, or do you want me to go through it as well? Any ideas? What's the auto stop? That's weird. Cool. You guys are very quiet. So is that I don't get it, or is it I'm dead because we've been going for 4 hours or 3 hours? How's it going? Just checking in with you guys. Are you guys all following, or are you guys confused by anything so far? Yeah. So do you all understand the expected value is just the? If you had to say it in one word, what's the word? The average. It's just the average, right? So then the variance is, I'm gonna have to stop very soon, but the variance is, I'll just tell you quickly about the variance and then we'll continue. So next week we're gonna solve this problem because we're not gonna get all, Thursday if we can, we'll solve this problem, okay? But in order to solve this problem, you'll see why random variables are important, and we'll also need to talk about continuous random variables, which is because you need a continuous random variable to solve this. Does everything I've said give you an idea about how you might go about solving this problem? Or not really? I have no idea so far?
Yeah.
So, like, any idea how you might start? Okay, so let me give you a hint. You know, so I'm gonna give you a hint to get started. But imagine this is the set of all the places where a single needle could land. Right? This is the set of all the places where the single needle could land. Yeah? What parameters would you need to talk about? You know, we're gonna organize them in a nice way, right? So let's do that. We can organize them in a nice way. So if I was to go ahead and do this, could you all agree that I could sort of choose the distance from the nearest one? I would choose the distance x and the angle theta. I'm going to give you a bit of a hint here. So if I chose the distance x and the angle theta, do you all agree that that's going to sort of lead to a thing? And there's going to be some portion of these, right, where there's an overlap, and there's going to be some portion of these that don't have an overlap. Do you all sort of see that? And then we can use the random variable, realize that all of these are uniform to solve this problem. Right, so I'm going to give you that as a hint. See if you guys can figure it out by Thursday. Just a fun little problem for you. Does everyone sort of see how that kind of works? So see if you can figure it out by Thursday. So it's like, again, you're going to need to define a random variable, which is going to be basically, you're going to spit out a position x and an angle theta. So it's actually going to spit out, it's a dual random variable, this one. So basically a position random variable, okay? And it's going to spit out two numbers this time rather than just one number. It's going to spit out a position x and an angle theta. Do you all get that? Just taking a specific situation, it's going to spit out where the needle is, and then it's going to spit out a combination of x and theta, and then given both of these, you can go ahead and put it into the random variable to figure out the probability. Okay, so this is the idea. All right, so I'm just going to sort of leave that there. So again, next time, like I'm saying, so next time we're going to go variance. Next time we're going to do variance and continuous random variables. Random variables. So was I sort of pumping you with a bit too much at the end there? Did you guys get a bit tired there, or how'd you guys go? Like, just be clear, because I could see that your faces looked a bit like I'm dying. Yep. So you guys, did you feel like you absorbed most of that, or how did you feel? What are we thinking? Because I just want to sort of change it for you guys next time if that's sort of what you would need to do. You were asking me for more questions, so are you like happy with these questions, or were you looking for more like different kinds of questions, or what were you thinking? More questions in general, yeah. So I'm gonna, so like questions like this, obviously, probably not going to see something like that in an exam, but questions like this you'll absolutely see in an exam, right? And questions like, which ones? Well, not those ones. Which ones would you like this? Oh, this one. Questions like this you would absolutely see in exam. Just be aware though, like I obviously won't give them an exam style until you guys are done. So next week I think we should be able to finish all the probability, or like next time we should be able to finish all the probability, and then we'll just do a bunch of problems on it, just like literally just problems. After that, I don't really have anything else to teach you, so right after that point it's just going to be questions until the HC. Okay, because I don't really have anything else that I need to cover. Unless there was another topic you guys wanted to look at, but I don't remember. Was there a topic? I think you said vectors or something, right? Proofs. You want to look at proofs. There's not really much content for proofs. I mean, for that, questions is the way. So there's not really anything I can teach you there. I mean, you saw the techniques I'm going to use, so you'll see that with questions. I don't really have much else to say. No other topics you want to look at though? No? Okay, cool.